Namaskar, good morning. Assalamu alaikum, Sat Sri Akal. This is Engineer Suraj Sen speaking from Bharat, India. To all my friends around globe regarding general topics of engineering management as we do every day. Management, which means professional management, and working management, which means we have to be very clear with that type of management, because without organization, without management, without establishment of system, nothing is possible to practically work in this world. This app indicates fellow. Other one is number 0183543, membership number, and this is Chartered Engineer India Bharat, and this is statutory body, Chartered Body Institution of Engineers India Bharat. I just tried to inform you about this. Before going for the talks, I'd like to first express my condolences to Engineer Ashok Manhar of Bhopal. Engineer Ashok Manhar of Bhopal, about which I knew yesterday through Facebook, that he has lost his elder brother yesterday due to heart attack disease or whatever disease. I don't have full information, but he lost his elder brother, who was assistant engineer in PWD of that area. I pay my homage to departed soul of Engineer Ashok Manhar's Chartered Engineer India elder brother, so that soul rest in peace. His brother was only 37, too young, and engineering personality, and we have lost one engineer from our country and from this world. I register my condolences to Chartered Engineer Ashok Manhar, structural engineer, civil engineer, for this great loss, and he must have stabilized his status, his soul, his conscience, his access, brain to handle this family. Hope he comes back in good state of mind. That's it. Thank you. Now we are talking of management every day, and this is quality engineering management. Organization and management, very important part of our life, and if we ignore it, we ignore a lot that should not be ignored. And we have to talk of soil, which is in itself a world of engineering, a different world of engineering, which is not given due respect and honor and value that it deserves, and it's considered only soil or something that does not have value, though we call, if someone puts hands into soil, and lucky one gets in return gold. That's one saying. And concrete and all engineering words relates to that. Very important one. And also FIDIC 2017, which is very much related to engineering world directly, though it's contractual world, but I'm saying engineering contracts, construction contracts and all that, which means FIDIC is a part of engineering. It's not isolated one. FIDIC 2007 is very much an integrated part of engineering world, without which we cannot deliver any works to public of this country. And I would like to say something just for 1 minute, and that is, regarding you may say sometime, regarding COVID-19, which is now being a little unorganized actually. It has been neglected now, but it's thriving very much, with much power. It's thriving, and I'm finding also some madness around world, and that madness is, I can say, among people of world. I think God's designs are very different. God just does something to teach humanity. At the same time, God creates minds of human, though minds should be in control of every human, but God's designs are very different. Sometimes when mind is changed by God, which means mind is changed by God, and human acts in that way, and that acting is really very difficult, because these are just my indexes, possible that briefly I am discussing, and these are, I'm doing my finger because I'm not able to share file yet. I don't know. It's my daily subjects, daily topics. My dear friends, when I say God changes mind of public, it is not something imaginary. This is factual, and it's that person, that human, who enters into problems because of that, when one ignores or one becomes anxious, or one becomes caught by anxieties, or mindless state. When one gets in, that happens, and that's what is happening now. COVID has told world that it's not same as being considered. It's very different, or it can be said that it is an extraordinary one, for whatever purpose we consider that. COVID. I'm not talking of COVID in this talk yet, just for information. COVID has made people mad. COVID is COVID, we don't say no. Whatever it is, it's very powerful, very strong. Yet, it is so powerful that it has affected minds of people. Minds of people. I filed one complaint with police in Faridabad about a week back. I usually walk and see people are not using masks. I had dispute with many people on road, and I asked them, do you want to go to hospital or you want to live? Means you are not wearing masks. I just assess that 70% people around do not care for all this. Carelessness, ignorance, working a lot. This complaint I filed, I got a call yesterday, and policemen actually wanted to tell me where people are not wearing masks. This question angered me. I asked policeman. He wanted to come to see me. He wanted my location and see me, and give in writing where people are not wearing masks. This is funny. I told him I usually walk on the road, and suppose I walk 3-4 kilometers. I see people, they are not wearing masks, and people. So how can I tell you where it is? You have police staff, you have motorcycles, cars. You go and see and find them. No, we are doing our job. Okay, thank you very much. If you are doing your job, why are you calling me? Oh, we want you to give in writing. This is not my job. I filed a complaint as a citizen. It's not my personal complaint. It is complaint for public service. If you cannot understand this, then don't ask me. I'm not going to talk to you about this. People are not using masks. Why should I even writing? You say audio to check. You impose fines. We are doing that. Okay, thank you very much. On behalf of public, you are doing that. What is this? I just inform you, people are not complying with this requirement. It's your duty to answer. Your people are sitting there, they are not asking anyone, they are not taking action, they are using mobiles. Are they paid for mobiles? What is duty of mobile by a policeman? What is his purpose of using mobile on duty? What is doing mobile? Same, I got news for Spain, people are there from Britain. There's Britain people and signs here as tourists, and they don't care about COVID. Oh, we are used to COVID, we don't care this and that and that. Same thing happened in America, same thing happened in USA, same thing happened in England, same thing in our country and many other countries. What shall you call it? I simply call it madness, lunatism, psychological attack, I call it. Despite knowing that millions of people have been affected world over, crores of people have been affected world over, and because the lakhs of people have lost their lives, still you are not serious, because you are not thinking, you have lost thinking power. You are so much anxious, so much enthusiastic. Oh, nothing, COVID is nothing, corona is nothing. We'll see, we know what's. What do you mean by that? I would just say, don't think that it's okay. Governments are fools. It may be British government, US government, or government of this country, Bharat, all. They have nothing to do with people of this country or that country. They are not interested in people, they are interested in their seat of power and economy. So take care of yourself. Nobody is going to help you. And particularly in this country, Bharat, I say, government is rubbish, zero, no action. You are your government, everybody is government here. As a citizen in your government, you take your care, you take care of your family members, you take care of your public, which you can, and be safe. That's it, nothing else. No, don't depend upon police, don't depend on government, nobody. Just serious in this business. I have to go on this only with. Thank you very much No more talks of COVID. I'm going further now. It's just instant today something. Outside management, organization. Yesterday I covered a lot on yesterday and day before yesterday. I covered considerable time on, you can say, on soil, which is very ignored. You can say it's ignored subject. Ignored in a sense, public don't care for soil. They don't understand anything about that. I won't blame public, not at all. Public can't be blamed. It's educated community in that world which should be blamed, and that's myself, my fraternity, engineering fraternity. Books are available. These are books. So this is a very old book. Books like this are available. I studied this book long back when I was doing my engineering degree. This book is thick one. How much? This book is having, I don't know how many pages. That time is having about 1,000 pages. The book has it. And in this 1,000, half or 40% pages are covered with soil. But who shall study that? We study from point of view passing examination. After that, I am an engineer. I am qualified civil engineer. I can do a lot. Yes, I can do a lot if I understand what I have to do. Just give me drawings, give me something, I'll do it, and that's all. Nothing more than that. Yes, it is. Soil, rock, what do you call it? What? Soil engineering we call it, rock mechanics we call it, foundation engineering we call it. We call it, we know it, still, but we do not have any degree of seriousness to apply it, this knowledge into our works, and that's big problem. Despite we have millions of engineers and maybe thousands or lakhs of engineers in our country and other countries, but actually this subject should be well known to everybody. We must have thousands and thousands of experts on this, but no, we don't realize that requirement. Somebody would come from moon or from sun or from Jupiter, and then that person would tell us, this is your subject, to do it. We are waiting for that information to know that this is our subject, our baby. But no, this is a specialized subject. You have to pass another degree for this. This is our obsolete mindset of this country's engineers and many other countries' engineers. Obsolete mindset. Structural steel is our baby, but we understand that. We don't understand soil as our baby, because this is superior baby on which structural baby supported. That point we can't understand. During my experience, I did not find that civil engineers, structural engineers got very much interested in soil, because soil is soil. It is rubbish, Who bothers about this soil? It is dirty, I don't want to sit in soil. I don't know, see, the soil has touched my shirt, it has touched my pant, or my shoes. See, my polish has been determined. Dirt, dust has come onto my shoes, or dust has come on my face. Dust is dust. This is what mind is. But you forget ultimately you have to go to dust one day. Whether you cremate yourself or you bury yourself, you have to go to dust one day. Dust is your permanent small cave in residence, or you will burn one day, so that will lead to fossils and dust one day, ashes. So don't worry about that. We are running away from reality of life. That's the only problem. We are running away from realities of life, which is really unfortunate state. A civil engineer means a soil engineer. In fact, there is no other meaning. If you are a soil engineer, then you can do foundations, you can do whatever. Basis is soil. Basis for basis, we say basis, foundation. But for that basis, soil, and for that below you go soil and soil and soil. Sometimes I feel happy with this, that people are so innocent, or they have run away. This is a very easy subject, soil. It's not very complicated. Complicated in the sense that you are not aware of that, that's why it's complicated. Otherwise, don't forget, people understood long back also. You may not be knowing history of Radford in Delhi. Some engineer told me, very senior engineer, once I was in Libya. I knew through him why there was a problem in Radford construction. Radford, that is in Delhi, there was a Mughal king at that time. What story says, I can't confirm this, I'm just referring what I was told and quoting that same. It was Mr. Engineer Jain from Delhi told that this king wanted that Radford be built very fast, and he handed over to that charge hand or mason or for whatever you can say, that person who was responsible for this, a pragmatic, experienced person, and he started layout and started excavation those days without machines and manual excavation, and it took a lot of time to do the excavation for Radford walls. And the king wanted to make haste. I want my Radford ready. So that person didn't say anything. Didn't say anything to king, and he just completed the excavation, dressed everything, dressed side, and then he escaped from the. Nobody knew where the guy is gone, and nobody could then further work on that because that plan was in his mind and how this could be done. Only that person was a kind of, you can say, referred engineer or referred experienced person. So time was not a major problem in those days because life was like that. It's time, okay, no problem, let us wait when it comes. Weeks left and months left and years left. And I think 2 years later, this guy unearthed, this guy appeared before scene and was arrested by king. Was arrested and produced before king. And king raised him. You have done a crime, why do you leave my building and you run away? That person didn't say anything, just explained to king, if you give me permission, I want to explain to you something. Okay, you are permitted. That person then explained about procedures of soil working. I'm just telling you interpretation of what it means. He explained to king that I was unable to explain or express in my language to you because I'm not where I understand properties of soil, that this is soil and this is near river, of course, and this is sandy soil. And I excavated this foundation for purpose of that, but until if we just do construction or in coming time, it will just sink. It's settle down, and your building will also settle down, your wall will settle down. So after I left, I could not explain that time to you because you would not have understood, and you maybe punished me. You might have punished me. So just to avoid that punishment, I escaped, and now it's 2 years over. They're having a lot of water through rain, otherwise, and whatever settlement it has to take, it has taken. It's now in that position. If I construct anything on this, if I construct some building or some wall or something heavy object, that will not further come down. Levels will be permanent, and that he explained to king, and king understand, and then he was okay. You are a very intelligent person, and he awarded him already. This I'm just telling you, the person. Those people used to think. Because those people might not be educated like we have university degrees, but they were having experience and understanding of soil. And don't forget that even soil properties nowadays we are using in cohesive soils that were not researched by engineers or scientists. Those were researched by agriculturists, because agriculturists are very useful, say for this purpose. They understand because they deal with agriculture, that soil itself. Agriculture understands soil, or you can say engineer understands soil. But engineers ignores this, and agriculturist does not ignore this. So these Atterberg limits, Atterberg was himself an agriculturist. You should not forget that. He used to understand soil, he used to experience soil, study soil, and he got that. He produced certain limits, 6 limits, and we use 3 of them, which is liquid limit, plastic limit, and shrinkage limits. Out of these 6, as I explained to you through books, we are still using for our engineering properties these 3 limits, and these are, again I am telling you, liquid limit and plastic limit and shrinkage limit, which are dominant limits in soil engineering, and you know meaning of that. If you mix water and soil together, 2n, because percentage of water is that high that the soil becomes flowing one, like river flows, or like some laminar flow, let us say laminar flow, not turbulent flow, and that's the quantity of water which is called liquid limit when just it starts flowing. And if you withdraw that one, reduce that quantity, and water starts flowing but becomes a paste, then it's called plastic limit. Plastic limit because that was liquid limit where this mixture becomes flowable, and in plastic where flowable state stops and it becomes sticky state, is a paste, a high cohesion. And then if you go further down water content, you start getting something else, that you further giving a value of strength to this space, and it becomes in a semi-solid status, and then solid status. You further drop down that. So there is some moisture left, and that's called solid state. These are Atterberg limits, We use them in our soil properties, and Atterberg limits is applicable. This is what for cohesion soils, not for granular soils. Means we have granular soils, just like we call sand, which is fine soil, of course. We can say just river sand or pit sand, and also rock. You can say rock dust, or you can say also that though there's a difference in that, we'll discuss that difference. But granular size, why I'm saying, or you can say limestone, for example. This is a limestone crushed. You can get, it's granular also, but only this I'm talking of size of grain. I'm not talking of properties of this, because there's a difference in properties of cohesive soil. Those silt is cohesive to some extent, clay is cohesive, but sand is not cohesive. Similarly, rock dust is not cohesive, and you can say dry limestone, dust limestone, or and there are certain clays which belong to both categories. That's clay cohesive. It belongs to it belongs to volcano, or it belongs to some other rock. So we can say soil is something, or rock is something, soil and rock, which are very basic materials of engineering, of civil engineering, because civil engineering's exclusive material which is used or automatically available all over the world is this soil and rock. No one can change it, because this is natural, and we remove that natural material, we make our foundation, and then we make superstructure on that. So our foundation again rests on rock to transfer its superimposed loads to foundation, and then to soil below for purpose of dispersion into soil mass, which is still unknown in clarity how it works. But that's fact that soil is used as permanent material, and we can't control that material itself, because even if we know relative property of soil, I am calling relative property because we don't know real basic property of soil. So soil engineering or soil mechanics also gives us reference properties with factor of safety considerations, safe margin consideration. You get this from soil engineering studies, or you can say soil is engineering studies, because you cannot say this is engineering soil or non-engineering soil. Soil is soil. It's used for engineering or used for something else, for agriculture or whatever you can say it's called. You should say that soil is a dominating material which we ignore, and in material science it should not be ignored. So I take it very seriously as an engineer, issue of soil, because your structure on which you have done a hard work, or you would do hard work on every structure for purpose of design, for purpose of is best use of materials, and for purpose of lifelong use of structure that you make on this, you produce, and that rests on your foundation, and which rests on your soil for purpose of transmission of all imposed loads and dead loads, all loads onto soil strata below. That's basic requirement of engineering, and soil is fundamental engineering, you can say. You cannot say it is elementary or is something. Soil engineering is fundamental one for civil engineers, for structural civil and structural engineers, I call civil engineers, and for all other engineers as well. Though they had no limitation to study this, but we have to give them a foundation ready for mechanical plants or ready for something else, even for rocket science, for space launching of these rockets. Foundation is prepared, pad is prepared. So it's done everywhere. You construct a bridge, you construct whatever structure, high-rise building, or you construct tunneling, or do whatever, sewer line, water line. Wherever you walk in world of engineering, in world of development engineering, I should say, civil engineering is basically a development engineering. Basically, civil is a misnomer, I can say. Let us say misnomer or no misnomer. This is human engineering, because this creates products which we use, all we use, without which you can't say. You use your home, you use your office, your road and infrastructure. You cannot go without that. So I say we have to think in different perspective, because perspective leads to prospect. And what I understand this is, means just for explanation purpose, just to awake you people who are sleeping from soil viewpoint. Yes, it is very boring subject, I agree. This is subject which is not a subject for engineers, because engineers expect subject based on calculations. It involves immense formulas and you can say data, so that you can just take out best one and use. But soil engineering is not that. Mechanics is not that. We do not know, because these are all natural products. We can't produce soil ourselves, just like we can't produce water ourselves. We have to keep this maximum valuable point in us. Soil is considered very useless material. People ignore the dust out your floor, and there's a dust in floor, that's why you say dust out. Soil is a gigantic material. It's available everywhere in world. There's no place, even in sea there is soil. We call them basaltic rocks in sea. If you might have heard, if you not heard, these soils are basaltic in sea, and that basalt means that basaltic status we call basaltic rocks, just like we call igneous rocks, sedimentary rocks. All these rocks we call this soil as basaltic rock. And this which is located at around maximum 4 and 10 meters depending upon sea and ocean depths respectively. We say 4 meters maximum for sea, and that's rock bottom level, whereas for ocean this is 10 kilometer, that is rock bottom level. This point we have to, I'm not saying exactly it's 4 meters, this is what I studied in geology. Approximation is that, and it's not exactly 4 meter everywhere, because we know from sea water level this goes down in curve form, and maximum it reaches 4 kilometers depth. And all these rocks wherever in below say, basaltic actions are there, basaltic contents are there, salt and water that enters from river to sea, that is not salty. But when say what is mixed up, it moves down, up and down into, and all sides from rocks are released, means because pressure, due to pressure, that much pressure, varying pressure from one started sea level down in the curve from to 4 meters or to 10 meters, wherever bulk basaltic salts are available, maybe not exactly at sea level, but if you go down further down and down, certainly meet basaltic rocks, and that salt is that's very crushed state, because if you're considering hydraulic load of water, hydraulic pressure, vertical pressure of water on that surface of rock, if you calculate and just conservatively 1 ton per square meter of weight of water or pressure of water on horizontal surface, and you go down to 4,000 meters, so it is, you can say 4,000 tons per square for sea, and this is 10,000 tons per square meter for ocean. So you see that extensive pressure, and rock cannot take that pressure. There must be, you can say, part below sea, and which is justly, you can say, should be a mix of salt, mix of rock dust, and you can say it's in solution of rock, and that is we call basaltic water, you can say, based on basaltic rocks. So this is, but that's very strong, means it's like, it's not sedimentary rock, you may say. It is like igneous. It's the igneous mean it comes onto surface in form of volcano eruption, and that is igneous because of fire. Energy is converted to fire, and that energy is converted to fire because of various actions, dynamic actions within sea in relation to rock, and those the forces created by that movement of these plates and various other disturbances, and which causes failure in equilibrium at certain locations. The energy produced push all water on ground itself. That's called tsunami, and if you say on ground itself, there is a pressure, heat, temperature rises within the surface of earth, and there is an upward force and eruption of volcano. So we can say these are all part of soil. These are earth rock mechanics. It is, and there are so many zones in world where you can say these faults are available, folds are available, and plate tectonics. You must have heard all that. I'm not going to that stage because this is not that subject. That's a part of applied geology, which is a very interesting subject. I was fortunate enough in that age I could not understand, but I opted for applied geology, and I was very happy with that subject. It was a very boring subject. When I used to start reading, there in half an hour course, snake does that. No, this is not very boring, and we are used to calculation activities, in particular in engineering. And if you find calculations by numerical something, yes, apply this formula, put these parameters and get answer. That's the easy one. But there's no numerical, there's no calculation. Such a subject solved is very boring for every engineer or engineering students, and I was also to that. But my nature was different. I just wanted to understand, read that. It's very important. There are very mechanical, very chemical terms in that, very, you can say, geological terms, which is very, very difficult name of rocks itself, or difficult the chemical composition of rocks in that. There's so many hundreds of names I used to write again and again to remember, and then only you can say. But I was lucky myself. I studied the sort of self, like I studied social science. I studied many researches myself, and really there was no tutor for them. I don't try on to find tutor for them, just books for enough for me to read. And though books was not explanatory, but just means see, if you read again and again, you'll find answer. A student does that, means to know something, you read once and second time and third time or fourth time, and you see by writing and you get that. So it's soil world. I welcome soil world into my life, and I feel that this is your basic world of engineering. Run away from this means you lose something if you run away from this. It won't help you develop as civil engineer. Only whole your life you will be perplexed. Means what I am doing is right or not right. That should not happen. Civil engineer means still you are engineer. Civil engineer doesn't mean perplexed engineer. You may be whatever qualification, but if you are not sure of your activity, this I learned from engineering from my institution, that is Institution of Engineers India, where examinations are very, very difficult in comparison to university examination of regular courses or formal courses. It may be, but there our system is very excellent. I can say that they do not want any misconception or wrong conception. If you don't know answer, don't do it. If you have clear conception, do it. And that is what basics of engineering requires. Engineering does not say you lose 60%, 70%. Engineering does not permit that. Engineering permits don't do it if you don't know it. Find, try to know everything. Try to be confident 100% that you have complete information, clear information, unambiguous information, reliable information, safe information, serviceable information, information that must be made of based on facts. If you have that information, only then you proceed for engineering. Otherwise, don't waste material and don't waste. Or once you do something based on just imagination or just thinking that it may be right, may not be right, don't take chance, because you're not doing research, you're doing work. And if you waste material, natural material, your money is wasted, material wastage, time is wasted, and then if it doesn't work, you have to do it again, rework this one. That's what I don't recognize, I don't accept. As an engineer, it's not my statement, I'm dictator of that, I'm dominant on that. I'll say, don't do, you do, but you have to check your confidence level. You have to check whatever work you are going to do. It should work. That's more important. If I am going to site a building on such soil, I decide to do that, then I must be sure I understand that soil. Soil is to be understood, soil is to be felt, soil speaks. Just like we say car speaks, soil speaks, sound speaks, we speak. Speaking doesn't mean voice. Speaking means telling about yourself. Soil tells us. Mind tells me, soil tells me. If I listen to soil, it tells me. Just like if I listen to structure, frame, it tells me something. Only engineer can understand that language. Just like we say, we understand graphical language, we understand drawing because drawing is a language, notations are language. Similarly, soil tells me everything about itself. If I want to talk to it, do we talk to that? That is my personality, my criteria, your personality, your criteria. If you talk to soil, soil would tell you everything about this. If you really talk to it, otherwise it won't say. Always there remains some confusion among engineering community, engineers. Some engineers even don't understand what is soil actually, what is basics of soil, what types of soil is that. Even that point engineers won't understand, and many like that. I can say very few engineers in civil engineering fraternity understand soil, and they understand everything else. They understand big books and they understand big theories and big software. They understand everything. High-rise structures they understand. They understand every complicated detail, but simple details are out of understanding. Laboratory engineers or technicians or scientists who are sitting there in laboratory, who are giving us information about soil after investigation and soil exploration procedures, they give us something according to their mind. They because nobody questions them. If you question them, they will answer you. If you don't question that, whatever they write, and you say, okay, because you are recommending, I'm following this, that is not engineering answer. Because that soil responsible person, head of soil laboratory, writes something to you, and if you don't question, you accept it without obtaining any clarification. If you have doubt, I can't blame those people. Those are human beings. Yes, they issue very big reports, like books, Some report is 200 pages, some is 300 pages, some is 400 pages. They do that. It's their profession, means they project like that. They project their profession, and valuation of profession. They try to satisfy everybody. They issue some speaking reports, and everybody should understand that's one point. That's a great point. I don't mind that. That's a good one, that they should give you such types of reports. What's that? Oh, it's not there. My that is from there. Okay, no problem. I'll take this one here. So this long talk about soil is not that I know about this. I am like you. I'm not different. Don't think that I know everything about soil. No, not at all. Yes, just like you qualified as part of subject, I too, I'm not expert. And I can't say even if I am expert, I'm expert, because I do not know everything about soil, just like every other scientist, every other engineer does not know. And we cannot know whatever soil we are talking about surface. Maximum 10 meters deep, maximum 20 meters deep, maximum 30, 40 meters deep, up to which we can drill and find what soil is there in form of bore logs. We can't even go in mass excavation of that, because only bore log is sufficient just to tell us what is there up to 50 meters. One bore log only in that area, not in other area, and we tell that laboratory people, give us a bore layer, go there, depending upon our location of building, our layout of building. That person doesn't decide. So we also give details about what sort of building it is, what purpose of building this is, how many stories it is, what is size of that, and maximum. Well, weight is not an issue here. When you say this type of building, they have an assessment. It's hospital building, it's an industrial building, it's residential building, it's institutional building, or it's a dam, water resource, or it is something else where in-depth knowledge of soil is very much important, where it's not simply surface spreading of load like tracks of railway or roads, where only CBR is important. But when I'm talking of in-depth study of soil, means it's there, because we should have information from borehole what this soil is, so that we should know. Maybe we go using piles for that. So pile may go up to 10 meters, up to 20 meters. So we should know that information, whether our piles would be sufficient, or will have enough strength in pile, bearing the strength of point strength, rock is socketing in that. Means we have to think that way. Sometimes I've seen piling in for 2 or 3 story building. You believe that? Some buildings in Abu Dhabi I've seen, commercial buildings, those buildings having 4 stories, 5 stories, 6 stories, 8 stories, and even sometimes 2 or 3 stories or 4 stories, and piling was done because of strata, being weak strata, and here as adequate strength is available, only soft rocks or medium rocks at that level, or the piles have to go to some level and depth, where due to friction at surface of piles and some by point loading. That load of stresses from buildings to be transferred into body of soil, not just leaving at 1 meter or 2 meter depth foundation, spread foundation. There have been cases where you can't use soil at surface level, or you can't use at shallow foundations. So it has been cases, but there was a case in Abu Dhabi. It was Abu Dhabi where I got a design of a villa. Villa means just 2.5 story building, not more than. This is generally called villas or kothis in our country, bungalows you may say. There was a bungalow or villa in Abu Dhabi, and I got through that design, and it was giving pile foundation in that. I was not convinced with that nonsense it is. I talked to general manager of that company. I was the chief engineer there, so he was dealing with generality of administration. So I told him, this is not correct. This is illicit. And then I researched through. I reviewed the soil report issued by reputed laboratory, soil testing laboratory. I just discovered from that recommendation or observation about soil testing. They conducted plate load test, and the report indicated that this soil would take 10 tons per square meter safe bearing capacity. I just period that point, and I made a letter. I drafted a letter to that consultant designer. This was ardent consultants. I'm just giving them because there's nothing secret in that. And also, is this gentleman said, no, this is rule here in Abu Dhabi. This gentleman unfortunately was not from engineering fraternity, but sometimes people are given charges like that. I was new there. I was not very much part of that company by that time. I asked him, this is not correct. He said, no, this is Abu Dhabi. This is a rule like that. I don't believe this is a rule. Show me where it's rule. There's nothing as such. When it's given in the report 10 tons square meter and saying sandy soil, what's wrong with that? Why you want pile foundation when 10 tons in soil and 2.5 story building doesn't give you that requirement of pile foundation? Why are you wasting time and material in that? I made a strong question. It is a strong question query to consultant. Why don't you just redesign and remove these piles and just use spread footing or something else like beams? So that consultant changed design, and there is a question, we'll charge 5,000 for this. Well, that's fine initially, this is a change of design something. It was designer's fault. Why did the designer accept for pile foundation is not required? Why are you spending money unrequiredly? Redundantly you use rubber. Well, this was not a big issue for 5,000 at that time. But question was, we could save time because piling takes time, and you can save that time. 1 month at all, to more than 1 month you can save that. So we changed that. Means we have to be sure about what we are doing. If you have good information from soil, what happens actually, people just get reports of soil, and I don't find people study that. Even this happens because on multinational projects overseas, there are every nationalities involved, and particularly those people who are at managerial level, even in technical, they are not qualified to that extent they should be. And quality people are not linked to designs. They don't care for design, and designs people are not, they are busy in their own world. They don't want to read everything. They want to read sometime when referred to. Otherwise, they say, okay, it's formality. We had to submit this design as a part of performance, and we say, yes, this part of contract we have done. If that is only consideration, and they say, oh, lab guy has suggested or recommended in that report, that's more weighable. But I mind that. I mind that. Job of laboratory is not to confirm what we have to do. They should not tell what we have to do. Yes, recommendation is one part, but that's not mandate. But we take it that way, mandate. That's where we lack in. It's our responsibility being design engineer or civil engineer of a building, because for me, design and civil engineer are no different positions. somebody classify that differently, but for me both are same. So that engineer who is responsible for that structure, it's that person's duty according to law, and not soil laboratory engineer's duty. So we must understand this point. You cannot say because I was recommended I am taking this parameter. No, recommended only. You're not instructed. You're not. That person is not going to take single point responsibility. It's your responsibility, technical responsibility, future responsibility, and complete responsibility. What parameters do you adopt from that? That's your job. Because there is no one point in soil that we decide, basis on which we decide. There are so many points. And moreover, always there is future uncertainty. I'm not saying for present. Future uncertainties. I'm talking to save a book, and I'm just giving some background so that we should understand value of soil mechanics or soil engineering. I should say that I was fortunate enough to little consideration about soil, because everywhere you can't do that, because generally on every project, if you are just a contracting company, you are having a design done by employer itself, and you cannot accede to those design parts, design references, or you can say basis on which your job is designed. You have to just follow whatever is given to you. So in that case, you cannot have an opportunity to refer to those documents, because this is not your scope of work. But when you are installed in a company where EPC work is going on or goes on, and you have every right there, then you can have access to those basics document, preparatory documents, design documents, where you can find a lot of information. And remember, it may be design or it may be construction. Just like construction, people make mistakes. They make errors in decisions or in interpretation of what they have to do. Same errors are often done by design section, and it's not their fault. It's fault of business commerce, because every team in design does not have only one project. Every team is loaded by 4 or 5 projects, major projects one time, because of commercial reasons. It's not that if you don't have 4 or 5 projects for one crew of design, you can say salaries and everything comes as a question. How shall you pay them? How will meet expenses of organization, establishment, that all those points come back. So I should not say that if you are working at 3 or 4 projects simultaneously, that what you remember 3 days before, or you maybe keep in mind, I'll take this later on, and you miss that point. Actually, this happens. So it's not exclusive. You can't do that. You do that, but you have overload of job, and once you decide, okay, you will take. We say, okay, at the moment I am taking this, I'll review it later. But that revision doesn't happen practically. And when there's a pressure of delivery of work, so what they do, they simply issue incomplete drawing, you can say, incomplete in the sense that it can't be implemented, and they simply put seal like issued for information, or in information means we may do like this, doesn't mean we are going to do that. This happens in our organization management. It's also part of management also, that this is only for information. Then also again and again the revision of the information keeps coming up, and then later on you get something else that this is for information. After that you say this book, something comments like that can also come. But once you get it's duty of a structure, I would say design engineer, is to issue actual design. But what happens, they convert same thing after little amendments on that issue of for information, also for issue for issue for construction, and they forget that point, why, what they missed, and this is natural. Means today I am working on that part, maybe after 15 days somebody else takes over me, and that person works. So errors are, not something miraculous. Errors do happen, and this error causes problems. When we design something, we have to keep in mind that design is not for decoration purpose. This design is not cosmetic. This design is for producing something physically in field based on information which 100% you also don't have, based on soil parameters which you may not be having at that time. You start working on those results, and you see always foundations also issued as informations, and it happens that those foundations people start working at, because until there was no system. Even now, if that design is not superseded formally and issued updated design, people use that. This, who bothers sometimes? If everybody is in a hurry, they want to do job, so soil part is always given third degree value. Moreover, person is different here in soil investigation, and other person who reads that report, probably he just reads for happiness, I see happiness, and not for implementation. This happens because one who reads about soil, he at that same time also studies foundation, and revision which should be done, review which should be called design review, which should be done. Well, I think it's not done, it's not really done, and that activity of design review has been converted to proof checking. And I don't accept that proof checking, because who is after all checking that? Point is that somebody empowers some professor, somebody empowers someone else, but only proof check can be done by engineers who work in field, who work in designs, who actually know what they are going to do. If I don't study soil report, I don't study what I have to construct, what is criteria behind that. If I don't study what this performance should be, I have no actual right to certified proof. If I do that, well, for signing it's okay, but is it really engineering? My question is that. Once you can't, yes, if I ask some professor about soil, he would say soil is very important, one top one. If you miss some, yes, they would say like that, because they read books every day. They teach students every year. Without reading books, they can't teach. That's also true. You may be house or big, but for purpose of teaching, you have to refer, and you have to bring so many references for your students to explain to them how it is done, what is done, why it means. Students require inculcation, and that inculcation professors give. But professors only write up to that limit. If you talk to them beyond that limit, they won't be in that level. Because their job is limited to teaching, while engineer's job is not teaching, engineer's job is to giving done product, they give completed product. So that product is identity of engineer, and that product is performer, that product is achiever, not engineer, that product. If that product performs, engineer performs, and that product does not perform, engineer doesn't perform. This is basics of designs and implementation. Now coming back to say, I was just diverging away from that. My issue is soil and soil management, and soil, you can say, as I say, management or organization or establishment, whatever I say, Soil is mother of everyone, father of everyone. Because without support of soil, just like without support of parents, you cannot start your childhood. You cannot grow yourself until your parents do not help you. Help means your responsibility, your baby of your parent. So my parent are, buildings parent are, structures parent are, foundation soil on which it rests. Well, I don't reject if we take some part of soil also as a part of foundation. If you can take in machines, designs, you can take in buildings also. But that part is because very little one if you compare to size and weight and forces building coming up. It's considered very, very little. Just like it happens when we consider foundation design. We simply assume let's take 10% of weight of structure, load of total structure of this footing on which this structure is going, whatever load is coming there, we just take in calculation say 10%. But when we actually design foundation, find it comes to like 15 to 20% of the structural load on this. So even your assumption is not exactly what's shown. If you take 10% means, and if we are taking 15%, 20%, oh, this will increase weight of this and this will be uneconomical. But we are taking already 20%. If you just survey that, you just quantify that in some cases, you will find a load of structure and its relation to weight of foundation approximately is that. So already you are taking that. So you just, oh no, just don't take more than 10%. This is not engineering wise right because it is not 10% that is big. No, there's only pro rata, you can say protocol. What protocol means? You should take actual one, in fact, working one. Well, that's different as a design part. You know much better than I know because you are structural engineers, civil engineers, so you use software. I am not very good in software at all till now. But design doesn't mean software, remember. Design does not mean modeling, running analysis, running design, or whatever parameters we give to each other, whatever assignments we give to this, however we do the modeling. That is procedure of the design basis, even not not calculations. You can do manually also that one. Of course, it takes some time. This software is not everything, but it's a tool we can use if you understand design. If you know that what this software gives you is reliable, and you can do that only when you know what answer should be there. Every engineer knows answer of what we are designing. We cannot say that this is automatic. If I am an engineer and I am going to design a beam or a column or a frame, then sometimes we also the sizes of members. And particularly I say I use Keynes. I'm not very good designer. I say use Keynes rotation contribution method, and I start that one. If I just go on box, I want to consider sizes of members like beam size, column size, and that slab size. I may not consider directly into my analysis, but it should be. It should be. It's better than not having something to have something. It's, if I don't take that into consideration, design would be there, analysis would be there, but when I have to do design, then I have to consider that. But if I take that into analysis, just like StatPro does or ETAP does, means they consider sizes also. So in that case, at least self-weight, or you can say dead weight would be considered. That be considered by design itself. And particularly, parameters, or you can say contribution factors, rotation contribution factors that we take into our design moment distribution, which is also Keynes rotation contribution method itself is a moment distribution one. So it considers into its rotation of the size members. Because of those size members, we calculate I and all parameters required, and we reach to distribution factors. including displacement factors of columns. So we use to that level. So we find those people. Means our sizes of sections or members, and you can say beams, whatever we can take, this can be included in that trial design. I call it trial design. So, and that's very, so means we can assume, or we can leave it to that and just don't consider that section. Later on we take that one. That's why I'm saying means depends on what quality work you can give. So it's okay means everything is okay. When I'm talking about soil, means soil should be well understood. We should devote time to soil, and very simple actually. If you understand soil, if you have clear conception, soil is not difficult. And if you are not clear about soil, it's a difficult subject. It's more difficult than theory of structure or structural analysis. If you don't understand soil, the whole life you shall stay in mix up. There will be something written, you will not understand what is that, and it happens. Means we should have clear conception of soil. This is not big deal. We have very good conception of soil. We just keep 3 or 4 points in mind. Means soil can be granular or non-granular, you can say. Well, that's very simple one. It should be granular or it should not be granular. When we are saying granular means some kind of grains are there. Grain like wheat, like rice. If you take them in a fist, they will all go down. So grains do not keep themselves intact until there's something else to cement them. If you take some grains in hands, you take some sand in hand, or you try to make it a ball, you can't make it. You may take a ball, but it won't be. It will try to come out of your palm. So this is sand. Other one is opposite to that. Opposite to that, and it's enemy. So if it's opposite to that, certainly it will be enemy. So sand is where they can't make a ball. There's another way you make a ball, and that's called clay. Clay nature soil, be clay or silty clay. And so these are two candidates, you can say, enemy to each other. One is in this direction, other is that direction. Both are different. These are actually basics, I'm telling you. If you understand these two, you will, because there's a lot of difference in these, properties are different. We take soil, sand, and put water in that, water come out. You put water on the other one, and then make water won't come out. This keeps water in because of porosity, and that because of permeability allows water to go out. So permeability and porosity is not holding itself, holding itself. And this is having angle of repose, that's not having an angle of repose. Maybe it is 90 degrees sometimes, so it's not considered. And work, friable, we can say, it can be fried, it can be fried. If you just fry something in fire, this grain, you can put that in, and it can be heated up. But that can also be heated up, but it can be fried. As a lump of clay, you can say. Water remains in there. That may dry it out, of course, due to heat. Water can be dried out, but after drying out, you can say what volume is reduced. We understand, or what volume something. There are various ways. So sand and clay. This is basics of there's silty and there's silty clay, then say maybe silty sand there, or there's some part that in, and there are two ways, means sand, also called fine sand, coarse sand. Fine sand, I mean to say, for example, if you take rain from sewer, I mean to say river bases, it's very fine one, means not like pit sand which is having coarse grains. So when you have different types of that, while you see in clay you don't have grains, there are grains, I cannot say it's the particles, very fine particles. You take let us say particle of particle of clay, variation is there to 0.002 mm to 0.0002 mm. See variation, 0.02 mm 0.02 means 2%. 2% of 2% mm, you can say 2% mm. 2% mm to 0.02% mm. This is clay size. How small this is? 0.002. This means if we take in unit 1/2000. 1/2000. You can see. What's that? What's that? This means you can't, if you take one particle of clay, though it's not easy to take particle of clay, even if you take dry clay in your hair, rub on some surface, it will spread to many centimeter square. That's just the same thing we say, you can say, specific area of some material, that material. A specific area of sand is not very little because it can't give that spread. But clay shall give you a large area, and just like cement does, fine material is cement, and if you say it's very fine, means it can spread to as much area possible. That fine, that's you can say that's the higher side, higher end of, this what you can say, fineness of what I said this word just now. Specific area, specific area. So as much as specific area one material has, that fine it is. If you take river sand, it won't work. You say pit sand won't work, but say cement is not soil. It is. I'm just giving an example. Composition of this specific area. Clay gives and dry. Size of coarse or fine sand or coarse sand is still higher. When we take range of 0.002 to 0.003, and this can be silt range, clay range, and 0.02 silt range, and you can say 0.05 for example. I'm just giving an example. This could be size of your coarse grain, and just like we say, then coarse aggregates. We say coarse aggregates. So these two materials I'm just comparing is, one is the coarse, or you can say the granular soil, and this is non-granular soil, or this is cohesive soil. We use term cohesive because it's same material is with each other. You cannot separate that. But soil is just, if you take soil here, it will come down if it's dry, and if it's not dry, it will remain in hand, but in controlled form, and make a ball. If you lose the well, the ball and break. That's what soil is. It will take soil in hand and water mix, and then you dry this, all water will come out. And same thing you try with clay ball, and to it will stick to your hand but won't come down. Water won't come down. That's different. So we find these two are not happy with each other. Clay and soil and sand, they are not happy with each other. They don't stay in same world. Both are different. Water, one retains, one doesn't retain. That's major difference. You might have noticed if you just walk sometime in rain, heavy rain, on some sandy surface, which is loose sand, water doesn't stay there, just moves down. When you walk on the surface clay one, just like you are passing through a field, or you passing through some area with a clay, you will find that within 5-10 minutes all the area changes. It's a very dry one day, till 1 hour before we said just a storm, and immediately rains, they are saying. All that sand or dust settles, and this area is converted to like slush, You can't even walk on that. You call it sometimes slush, or you can say, and you slip on that because because of water, volume of that soil has fallen, it's increased, and that doesn't have any shear value at that time, shear standard time. So we have to understand this point, that both these are basic points. I'm just telling you, these are basic soils. Actually, these are basic soils, and these have come not only from one source, these come from. For example, clay doesn't mean it can be only, it can have various forms of its origin. It can be volcanic clay, it can be sedimentary material or other clay, it can be clay from different sources, and depending on size and porosity, it happens. So if you understand these 2 points, you can understand half of this. Then in relation to these are limestone, sandstone, because sand means it gives consolidation or after interlocking. You can see there is a varying grains in this, because grains can't be of same size in nature. You cannot say that nature has same size of grains in practical work. We can say differently that this is uniform or this is one size grain, but actually there is no grading. And that's why it's called grading. We say nominal size is this, but its real size is different. Just like we call 20 mm nominal aggregate, it doesn't mean aggregate at 20 mm. Yes, if it's a one size aggregate, then okay, we can say maximum size is this, but in that it's not that. So, say I can say it's a granular size of 20, there will be 24 or 20 or 18 or 16 like that, depending on maybe something like that, not dust. Same, clay is having one size particle because it's actually not having any strength. Soil particle has sand particle has strength. It's maybe globular or different size. It can interlock, it may not, but it shall have voids in that. It shall have voids in that. There are voids also in clay, but there's water in that, there's air in that. But in sandy soil, there is no water. Even if there is water, there exists water in that, it will come out, it will dry out. So each and other properties are opposite to each other. You can say we can compress both, we can compact both are compactable. But we need more energies on clay soil, but that energy is limited also. But if you take other side of this, if you just pour in some pit your sand in dry form and your pit is full, then even if you put water, there's no meaning of that. It doesn't require that level of compaction. Yes, if you want to compact it for purpose of ramming, for purpose of compactive force, you have to keep it wet for some time, and then you can compact it once it dries out. But that one is very difficult for compaction. Compaction and consolidation are very, very top priorities. Properties that we have learnt in. Compaction is packs in, it packs in something, it gives upward value to that. That point you have to understand. And when you say consolidation, this is very long-term process. It may take 50, 60, 70, 80 years, and it becomes more and more dense and stable. And that's why we say if soil must be very well understood, because soil strata has been there for hundreds of years maybe, and it's already consolidated in. So we have to take from that action. All results come because of that. So it's where we are talking of soil engineering, and soil engineering is beautiful subject for every civil engineer, but I'm not finding anyone interested in that. I don't know reason behind that. People are more oriented on soils, and they don't do it because this is a fact that generation has changed, and engineers are more interested in StatPro use or ETAB use, and they are getting ready-made food. So why should they cook food? Point is that they are just buying food and eating it. They are just feeding in. They are raising modules and they are running analysis and design, so they are getting answers. So why should they work more for that? And that's the only reason that you are depending on software rather than software should help you. You are using software for X, and of course it does because you are not doing something else. It's all like that. Dear friends, my purpose is not to discourage you. Well, I see two friends are there, this soil and this soil, and then there's the soil which is extension of both of them, sand soil, sand rock, and maybe clay rock. There will be rock of volcano. Just like we classify our rocks, it's also part of soil. We cannot consider rocks separately than soil. Every rock is soil. And we know basically, fundamentally, in our system of engineering, every engineer knows this, that we consider three types of soil rocks. We consider volcanic rock, and we consider sedimentary rock, and we consider metamorphic rocks. You know that. And we know what happens. Just for information, I'm repeating, you know it very well, but for public it's important to tell them, because this is talk meant for all. It's not only for engineers, it's for all. But its question is, public should learn what we do. We learn that public should know what. I'm not saying public would work on that. They should know what's happening. When we say igneous rocks, what does it mean? You can say it's eruption of volcano, fire eruption of volcano, and igneous. Though it is English word, actually I consider it as another word. Agni, I-G-N-E, Agni, can say fire. So it is fire. Volcanoes of fire, and we in Hindi we call it Jawalamukhi. Javala means fire, and Mukh means crater, open portion of mouth. You can say face or mouth of this rock. It's called crater, not creator, crater. So that's mouth. So igneous rocks it is. So it was created by fire. So it's called igneous rocks. And there's another one. When deposition, what's deposition or sedimentation? That's another name of this rock is sedimentary rocks, or rock result of deposits for many decades, many centuries, and various layers of deposits can be seen by geologists when they research on that. And counting on those years approximately based on thickness of one layer, they can say how many years this layer to have taken for its thickness. And all thicknesses are different in this layer vertically, which means higher level, or can say higher thickness could be thicker, more higher than lower one, because of consolidation might have happened along with time. And you will find different properties of those sedimentary levels, sedimentary rocks, sedimentary deposits, and based on that, counting the approximate in one layer is this much, how many years must have taken, and how many layers are there, what's the depth of them. We just get assessment of age of these layers and total age of up to this point. And this happens because of movement of eroded particles due to environmental conditions, metamorphic conditions, or meteorological conditions. One particle moves from one place to other place, and it will go there, from there on to somewhere else, and then from somewhere else, and then some come from settlements, some come from regions. So they are that reason for igneous rocks and sedimentary rocks. For example, lime deposits is there, sand deposits are here. There are so many other metals, chemical words are there, but results are same, equivalence is same. So you can say sand deposits and this deposit and that deposit. Where deposits are there, that's called second sedimentary rocks, or you can say igneous rocks is not sedimentary, it's continuous mass, it's continuous common thing. It's not that we are saying it is, it's different. So what I mean is that now And the other one is, this is two igneous and sedimentary basics, and these are basics of rocks, like CAT, cat, and RAT, rat in English, or ABCD in English. Else you can say soil English, I can say soil language, that you must understand these are rocks as civil engineer, and how these rocks conduct, how this behaves. And then there's a metamorphic rock we call, it's nothing but it's decomposed form. It's transformed from sedimentary rocks. So sediments are deposits for centuries, and that rock, sedimentary rock, and then it's acted upon by temperature, by water moisture, or you can say by rain, by thunder, by solar heat, and by chemicals generally. So all these agencies work on top, and they work, and there's some point where you can say some water materials are available, some fuels available, and you should know that whatever actions happen on these sediments for times on every sediment, not only on your top sediment, a maximum happens on top layer, and also if you go down, it acted in those days when it was seen or visible. So that metallurgical action changes this sediment to based on metallurgical itself, metamorphic rocks. It decomposes its surfaces, it decomposes chemical composition, it converts into something else, some color change, some properties change, and this we can call that, this is metamorphic change, we call it metamorphism. Real effect on sedimentary rock due to weather effect and onto your areas of surface. So surface area of Earth is having different kinds of rocks, means all these three are basics, there are so many, but we are going to depend on these only. So generally igneous rocks is showing better position, we can say aggregate we use. Sometimes we say we have lime aggregates for purpose of concrete, coarse aggregate I'm talking of, lime aggregate coarse one, and we say sometimes igneous rocks aggregate. Both aggregates are available. Igneous is expensive because this is expensive rock, and aggregate of this are generally based on granite. We use them for different purpose. So rocks teach us something, soil teaches something. We have to only point that we have to remember them, we have to understand them. We should not think that we are nerds, we have gone mad, like that. So my dear friends, when I am talking of this extensive talk on soil, rock is basics as a soil itself. It's not different, the rock is different. Yes, rock mechanism and plate tectonics, all that, and lithosphere, which is actually, we call lithosphere here for purpose civil engineering, because air we are using for different purpose, not purpose of housing, using for purpose of ventilation, that's okay. First is how to live, that's more important than something else. Do we know living? No, we don't know living. Everybody stands in something and like that. Now, I'm not inclined to talk of this only. Soil, as said, sand soil and clay soil, very simple, and then the silt also of same family as clay of different sizes. If you understand these two, and then we can say, particularly by name, that this is this sand, sands, we can say this is this is sedimentary basics, and sand rock we can say. Certainly there is a consolidation of sand, that's why it's sandy rock. Sandstone we can say and we say this is igneous rock, so understood it's that rock. And metamorphic rock, or even the soft sand, or medium strength sand rock, or high strength rock we say. So we can say, if we see properties or reports of soil, we find various such information. And when we say, clay soil, you cannot say that clay is good for agriculture buildings, because you absolutely can do it. Sometimes, we ourselves confuse for nothing. Confuse for nothing. See, angle of repose. We have to think, how does it work? Similarly, we can say interlocking of grains. There can be interlocking of grains, but there can be no interlocking of clay, because there is no such arrangement in that. These are flocculent particles, and sand is having different particles, different size particles, varying grain size or uniform grain size. It depends what type we have. If we have uniform, that's not possible in nature. Yes, sometimes quarry people can give you that because by the skin sorting, but you can't use uniform size sand even, because it doesn't work. It doesn't interlock itself. Interlocking is a must. Interlocking can be done by varying sizes of particles. There's a void, if you use uniform size, there's a void, uniform size, then those void must be filled by lesser size, and that lesser size void again you see for the further lesser size. Like that we fill these each other. There is a complete matrix between my matrix. They have angular dimensions, some angular sizes of each grain. I'm not saying global, I'm not talking global size or angular size, interlocking size, so that this and limit to elongation itself means the particle size, so it should not be that long enough, it should be little one. And say, for example, in 20 mm coarse aggregate, we say elongation which is limited to 40 mm length of that elongation, we call it. It should not be more than 25% or 35%. When I was young, say they used to call 25%. You should not have elongation index more than that, but it doesn't happen. Who sorts all that? So they later I think it goes to 35%, and I think 35%. It should not more than that. And this is soil means how it should work, how it should structure itself, and that's what we are studying here: the structure of soil. The structure of soil is very important part. Is like the structure of building, framing. So we are talking framing of soil. Soil can be framed in, but it can be interlocked. It's possible. Interlocking of grains, uniformity of grains, grading of each size grains or combined grading, everything is applicable in soil. Then you can say we have a full range test of soil. We test soil in laboratory. There are many tests conducted on them. All those tests by chemical terms. We can say it happens, and then we do same thing for clay soil in laboratory. Rather than finding bearing and stress of that soil, finding that cohesive power, C value of C, that's called shear value, find on that. So varying properties are applied, varying tests are applied on this soil. So what I'm saying is, actually there are grain wise there are so many. Even then grain are this 0.002 and 0.002 to 0.002, which is main soil, and varies on every shape. And there's other one and other one. Sometimes clay itself sees on ground is very strong, because there is no water in that, very little water. And if you see that, walk on that, you find it's very strong. You walk on that, you my God, it's too strong soil. And you don't know, it's very good soil. Don't see this. Because things are back on, it's very good. See how strong is this? I can apply more role on this. It's much more better. Common answer is that. Common sense is that. This is called common sense, common comment. Because we know that personally, we don't know more than that. Everybody agrees with that. Yes, it's good. I talk to my friends, architects, and used to go to their sites just to look on that. What sort of, in the beginning they used to take some of my friends, okay, they'll see. I was irritated also sometimes because of that. Because those people think it's like kulcha chola, like some restaurant, go to restaurant, ask for dinner and take dinner. It's like that. They think so. I had dispute also with many. Use thumb rule. I told them, friends, I don't know what is thumb rule. You are so big MIE at the time now. Yes, I am MIE. That's why I am MIE, because I don't know thumb rules. I know engineering rules. If you are talking to me about engineering rules, I am there to help you. You say, no, I just do with thumb, then I say thumbs. Thank you, I don't know you. Soil is so forgotten. So forgotten. In our country, soil is not given any weight. Any weightage. In that type of world we are. But if somebody asks me, I don't do it. If somebody asks me, oh, you just use something and do it. I have seen some people, they are well educated, engineer educated. They don't care. They don't care for something, they should. But and maybe it's not their fault. I can't say it's their fault. We have developed such a rubbish system, such a hopeless system that we just believe in. And we say believe in, and believe in is the same thing, orthodoxism. Believe in is Western. We believe in, we have a reason to believe. Reason to believe. But here I don't have any reason to believe that soil is good. I don't have any reason to believe that. You may be having reason to believe, you believe it, I don't believe it. Why should I believe it? I can check it, I can make sure it is. When I get a confirmation, it can do. Confirmation is important, or believing is important. It's the point. Believing or confirm. Why do we say I believe in God? I say I believe in God because I do not see Him in sweat. I do not see that entity which says you believe in me. There's no entity. So soil is same, I don't believe in. Simple, I don't believe in. So I assume this, you assume that. Why should I assume that? I have to test it. And that test too is relative. We have to test it. And if you don't want to test it, then what answer I give you? Public is ignorant doesn't mean you should be ignorant. Engineers should clearly tell, I would not do this. But for question lies in, if one can say, other can say no, I believe in. Why are you asking me this? Question comes to that. Too much talk, soil. Let me just, let me go and see state of weather and come back after putting. I think I should give them their food, come back and see how it works, and also whether I make sure. Just a minute, please, I come back after 1 minute maximum. come back, just quit and come back. Oh, sorry, okay. So continuing my speech, I'm sorry, not speech, just talk. So I don't like to say speech because I'm not leader, and I don't say I'm speaking. Just conferencing with you, discussing with you is very important. Now, back to point. Soil again, and it's already around 2 hours, no problem. Work is work. We were talking yesterday, we talked of compaction, and we talked of compaction, I think, yes, we talked of compaction. So the machines, some of the machines. If I say that construction equipment, I go further, and construction equipments, I go further. Yes. Construction foundation engineering. Yeah, it's engineering properties here. This is about this starts from its page. Starts from page chapter 13 and page 522, and older pages in books are about, you can say, about 988. So about 45% pages go to soil, you can say. Engineering property of soil we have already discussed. Means most of engineering structures rest on soil, and most of them is why say most? So most of engineering structures rest on soil, and hence role of soil as a foundation material. See, foundation material. Remember, introduction. This is most engineering structures rest on soil, and hence role of soil as foundation material is as a construction material. As a construction material is outstanding importance. Outstanding is remarkable. All engineering structures such as building, dam, retaining wall or bridge remains in contact with soil, and many more. These structures exert pressure on soil mass, and development of structures happen due to interaction between structure and soil mass. That happens. Development. This means an engineer should be able to know and estimate about quantity of stresses and strains developed due to this soil engineering deals due to this. So what happens? Soil engineering deals with all problems connected with soil, movement of soil below foundation due to load of structure, settlement of foundations, etc., etc. This is what basic definitions say. And just for history, let's say soil mechanics as a subject, soil mechanic being a subject is rather young. Dr. Carl Terjagi published first book on soil mechanics in 1925. So it's not even 95 years. It's 20. So around 95 years have gone since we got one information. I know not of institutional information, but personal book written by Dr. Carl Terjagi who is not known as father of soil mechanics, and he actually gave concept of this new subject. So it was new subject in 1925. So we can say, for example, I studied in 1975 or say 1980, let us say 1925, something about that. So 50 years after that. So no subject can develop in so short a period. And it says further that although I know published source books 1925 actually gave concept this new subject. So is an exponent of soil, you can say, Dr. Tarjagi. Although some stray works have been done in field of soil mechanics and foundation engineering earlier than Dr. K. Tarjagi, but Dr. Tarjagi gave unified approach to this subject. Now this subject has assumed great importance because large and heavy structures are being constructed in the whole world on massive scale, and these structures pose new foundation problems. The solution of such problems can be done only by applying theory of soil mechanics. This is just introductory note. I'm not going to what else it says in formula. I'm not going to say formula because formula have all been now on, I think, on software. So I should not worry about that. Now what we talk here about soil is the basics one. Now also we will say that there's another one that's called, say determination of water content. Now that's not point I will discuss now. Particle size distribution, that's also very important. Particle size distribution says that which particles of various sizes on soil is essential for identification and classifications. Particle size analysis or mechanical analysis, can say this is performed for separation of soil into different size fractions. Sometimes it's also known as grain size analysis. Grain size analysis of a soil is due to two stages. Sieve analysis for coarse grained particles, and hydrometer analysis or pipette analysis for fine grained particles. In fact, soil sample contains both coarse grained and fine grained particles, and hence both tests are done for complete analysis. So I will not take test at this moment. I am just trying to understand theory first. Means that there is a law, sieve law. This is sieve analysis for knowing grains distribution, which can be according to our sieve 40 mm to 75 microns, and British sieve from 1.5 inch to 200 designation, and you can say ASTM sieve from designation 1.5 inch, same as this. So IS sieve says 40 mm downwards to 75, to say 40 millimeter aperture size down to 0.075 aperture size. That's for sieve analysis for granular particles, and then also for other one that is for from what you can say non-granular particles. I can say this is Stokes law. This hydrometer test, which can be silt or clay. The silt or clay, and their sizes can be determined only by wet analysis. So that is dry analysis, sieve analysis. That's dry analysis, and sieve analysis that's dry for coarse grained particles, and hydrometer analysis or pipette, you can say pipette analysis for fine grained particles. In fact, both must be done because both are available in soil samples. So these were two, Stokes law and the settlement law, and sieve analysis, Stokes law is very different. We can just read it just to understand. I'm not going to calculate that. A hydrometer or pipette analysis is based on the Stokes law. Stokes law is based on principle that spheres of different sizes, you can say fall through a liquid at different velocities. Space of different sizes fall through liquid of different velocities. Hence, grains of soil suspended in liquid water shall settle down at bottom, and its velocity will depend upon shape, weight and size of grains of all other factors are same. In vertical analysis, it's assumed that soil grains are perfectly spherical and its specific gravity is same. So coarse particles settle more quickly than finer particles. If single sphere is allowed to fall in an indefinite liquid medium freely, without any interference, then its velocity shall first increase under action of gravity, but in a few seconds it would attain a constant velocity which it shall maintain indefinitely unless boundary conditions altered. Such constant velocity is known as terminal velocity. If we terminal velocity is the sinking of a spherical particle, then it can be given following equation, which we will see later on. Now we'll just understand what is that. What is saying these are global particles, we can say spherical particles which settle down in liquid. Depending on size of these particles, in size is not exactly sphere, they may be different one. So depending on the size of particle, diameter particles is different velocities, let's say, it means different velocities and strengths of soil. Suspended liquid water will settle down at bottom and the velocity will depend on it's like that. It's called Stokes analysis, wet analysis, and I will see that one later in this. Sieve analysis, mechanical analysis, which just is granular analysis, we can say that. Then if we go further, we'll take longitudinal hydrometry analysis, and then there are so many other soil, hydrometer correction, and meniscus correction and dispersion temperature correlation. So this is just informative titles, informs I'm giving you. Just we studied yesterday grain size now. There's normally there's one grain size here. Calculation of particle size d in mm% after that. Let's say repeat analysis knowledge that will be clear. Plasticity index, we talked yesterday about this, and we talked about consistency index, liquidity index, we have to talk something like that, causes of plasticity of soil. Now let us have a brief of this, only brief, it's not numerical one. Liquidity index, causes of plasticity, what does it say, toughness index, and let's have a brief discussion. I feel this useful maybe. It says causes of, I'm not discussing at this moment further properties of heterogeneous limits, because later on I keep this plasticity index. I'm not going to discuss consistency index and liquidity index or toughness index or causes of plasticity. So I very one paragraph only, and this is Atterberg performed a number of experiments and found that quartz ground in particles of 2 microns and less diameter has no plasticity. Light is off again. This happens every day. So it says Atterberg performed a number of experiments and found that quartz ground in its particles. I think I have to put my exact one off, otherwise this inverter will come down. This is the problem with light here, If light is gone, I find problems. I have to go again and again to see what is happening here. which is my problem actually. We put off light of the Good Master Chaudhary Raju, welcome. Thank you very much. No. Just briefing this very small paragraph. Atterberg performed, Atterberg understanding was an agriculturist in Germany, and Atterberg performed number of experiments and found that quartz ground in its particles of 2 microns and less in diameter has no plasticity, while mica ground to same size particles exhibits plasticity, which increases with decreasing grain size. Later, Goldsmith advanced a generally accepted theory which explains causes of plasticity. According to his theory, plasticity is due to presence of thin scale-like particles which carry electromagnetic charges on their surfaces. Molecules of water being, bipolar, orient themselves like tiny magnets in magnetic field next to surface of particles. Those molecules of water adjacent to particles are bound by this electromagnetic field in an immovable state, forming a thin layer of solid water adhering to particle. Farther from particle surface, water becomes highly viscous like asphalt, or growing less viscous with distance from particle until at some distance ordinary water exists. So with enough water present, particles separated by molecules by molasses. Molasses like water which allows particles to slip past each other to new positions without any tendency to return to their former positions, without change in volume of voids and without imparting cohesion. As more water is evaporated, more viscous water separating particles increases cohesion and reduces plasticity, until eventually when clay is dried out, only solid or highly viscous water remains, cementing particles together in solid state. Correction of Goldsmith's theory for cause of plasticity can be checked by the fact that clay does not become plastic when mixed. Clay does not become plastic when mixed with a liquid of non-polarizing molecules like kerosene. Film of solid water attached to soil particles is called adsorbed water or double layer water. Now, I'll repeat this paragraph because this is technically very interesting. I'm not going to do calculations after this. Just repeat so that a more understanding comes in, because this is technical one, this is natural one, you can say soil philosophical one. I read again word by word what this says in causes of plasticity in soil. Now, in soil, Atterberg, again I am telling Atterberg limits because I talked yesterday Atterberg limits, and these were there. liquid state, plastic state, semi-solid state, solid state, and there was liquid limit. Liquid is where liquid state ends. In liquid state comes to plastic state. Between two state, liquid state and plastic state, that line is known as liquid limit, because from that line if you add more water it becomes liquid, and if you withdraw water from them it becomes plastic. Then comes plastic limit, which is between plastic state and semi-solid state. When you withdraw water it becomes semi-solid, and you add some water it becomes plastic. So that's known as plastic limit. And then between semi-solid and solid there is a line that's called shrinkage limit. Means if you add water to solid it becomes semi-solid, and if you withdraw water from semi-solid it becomes solid. So that line is called shrinkage limit. And then total volume of soil mass when solid states comes to origin. So there are three, and this is called soil mass total volume. So one is liquid limit, one is plastic limit, and one is shrinkage limits. These three are called Atterberg limits. Atterberg limits. Now the question is, we are talking of plasticity. That's why I'm talking about what does it mean actually. What does it mean as a plasticity? That meaning is very clear, should be very clear to understand soil, what soil is. To understand that, it's very important one. So dear friends, this now what again I said, this agriculturist Atterberg performed number of experiments, not defining how many experiments, but and found that quartz ground, quartz it's the material, quartz, it's the kind something in soil. Quartz we call it, quartz must have quartz cells, and like that you might have heard. Quartz, Q-U-A-R-T-Z, quartz, ground in particles. It's ground in its particles of 2 microns, 2 micron size of quartz you can say, and less in diameter, has no plasticity, less in diameter, 2 microns and less, 2 micron, micron plus 2 microns itself, 2 into 10 to the power minus 6 micron. Well, or less in diameter, has no plasticity, while mica ground to same size particles exhibits plasticity, which increase with demanding grain size. So it says that quartz ground in size of 2 microns has no plasticity, but mica ground to same size has plasticity, and that also increases with decreasing grain size. Means if you decrease grain size it attains more plastic. Later, means after this claim, Goldsmith joined, and the theory was which explains cause of plasticity. According to this theory, plasticity is due to presence of thin scale-like particles which carry electromagnetic charges on their surfaces. Molecules of water, one question is chemistry of that. Molecules of water being bipolar. Molecules of water being bipolar, then orient themselves like tiny magnets. molecules of water, bipolar, orient themselves like tiny magnets in magnetic field next to surface of particles. Magnetic field surface particles. Now what happens then? These molecules of water adjacent to particle size are bound. These molecules of water adjacent to particles are bound by electromagnetic field. These water molecules to particles are bound by electromagnetic fields of water field in an immobile state. Molecules of water being bipolar orient themselves like tiny magnets in magnetic field next to surface of particles. These are magnetic fields for particles. Those molecules of water adjacent to particles are bound by this electromagnetic field in an immobile state, forming a thin layer of solid water. Adhering to particles. It says molecules of water adjacent to particles are bound by this electromagnetic field in an immobile state, forming thin layer of solid water adhering to particles. And farther particle surface, water becomes highly viscous like asphalt, growing less viscous with distance from particle until at some distance ordinary when water exists. So with enough water present, particles are separated by molecules. Molasses means when with enough water present, particles are separated by molasses like water, which allows particles to slip past each other to new positions without any tendency to return to their former positions. Now, without change in volume of voids, and without imparting pollution, as more water is evaporated, more virus weather significant it's something very important we to think of. Let us see, to understand this theory first of all. So farther from particle surface, water becomes highly viscous, like asphalt, growing less viscous with distance from particle until at some point or distance where ordinary water exists. So with enough water present, particles are separated by molasses like water, which allows particles to slip past each other to new positions. Past each other, then to new positions without any tendency to return to their former positions without change in volume of wires and without improving cohesion. As more water is evaporated, more more viscous water separating particles increases as in the cohesion and reduces plasticity until eventually when clay is dried out, only solid or highly viscous water remains permitting. Now, this is about what says as more water is evaporated, more viscous water separating particles increases cohesion and reduces plasticity until eventually when clay is dried out, only solid or highly viscous water remains, cementing particles together in a solid state. Correctness of pronouncement is 30. Now, says cause of discussion goes with theory for cause of plasticity can be checked by the fact that clay does not become plastic when mixed with a liquid or non-volatile molecules like kerosene, film of solid water attracted to soil particles is called. Now called adsorb water or double layer water. Now liquid layer determination will do later on. It's not that you just wanted to know all this. Simple theories, that's more important. Again, plastic you can do. We were talking of soil classification yesterday, and we talked of what to do, what not to do, problems are. Now we are talking of soil classification. Yesterday we understood this. I just repeat that paragraph only for refreshing. Different types of soils having different engineering properties are found in universe. Efforts have been made to classify these soils into different groups having reasonably similar behavior. Different types of jobs need different classification systems. For example, classification system suitable for road project is not suitable for an earthen dam. So main aim of soil classification is to arrange various types of soils into different groups according to their engineering properties. Soil processing is similar characteristics can be. Now we can say soil possessing similar characteristics can be placed in one group. Soils classification can be done for different types of engineering works, but are mainly systems of soil classifications. But for general engineering, you can say soil classification can be done for different types of engineering works, but for certain general behavior of soils are common for all purposes. There are many systems of soil classifications, but for general engineering, soil can be classified into the following. We did grain size and we did grain size classification. And we have to talk of this classification about general grain size, in which is there are, I think, three, two, yes. This is grain size distribution. Grain size classification is number one. We have according to that. And so then grain size, and then we have to US Bureau of Soil. MIT is Soil Bureau of Soil Classification. There is the MIT and IS classifications. GBOI of MIT. Then US Bureau of Soils triangular classification we did yesterday. Then we crossed to heterodox limits, we crossed back limits. I'm sorry, not about soil classification according to एक ऐसे granulated plasticity chart we did, 6 locations, 6 areas in that, which were inorganic salt of high compressibility, and inorganic salt of high compressibility, and organic base, you can say organic clays, inorganic cities, silts of medium compressibility, and organic silts, and inorganic salts of low compressibility, organic clay of low plasticity. So inorganic salts of high compressibility and organic clays, and inorganic silts of medium compressibility and organic silts, inorganic silts of low compressibility, inorganic clays of low plasticity, inorganic clays of medium plasticity, inorganic clays of then you can say if liquid limit and plasticity index of the soil are available, region can be located on plasticity chart. Then we went on to public road administration of soil class systems. Let's say the public road administration like soil. Now we'll go to public road classification system. Now public road administration PRA classified system is based on mechanical analysis as well as attribute limits, and this system is primarily used for pavements. Soils have been divided into 7 primary groups, in this case 7 primary groups, which are designated A1, A2 up to A7. Such as A1 to A7 shown in table will show you. Group A1 has been divided into 2 groups, subgroups, and group A2 into 4 subgroups. Now, let me open this also. For 5 minutes, that's stuff like that. From CV analysis, a parameter called group index to soil is determined. Group index itself is not used to place soil in a particular group, but it is a means of rating value of soil as a subgrade material within its own group. I will repeat this. It says higher value of GI. Okay, this is okay. So it's clear. Soil in particular group means rating value of soil as the subgrade material within its own group. Higher value of GI, poorer its quality of material. Group index is dependent upon liquid limit, plastic limit, and amount of material passing 75 nanometer. It can be found by following equations, and this will see what is that. We'll get on see. Let's go to see something now. Here is a table that is public road classification systems for soils. In this, there's a general classification, then granular materials, and then silt clay materials. This is general classification. This is classification systems for soils. Let me show you on computer better, because projection is better. I don't have a projector here, so I can use directly the focus projector. But move this way. Because seating orientation is a problem. Now, once again, I come back to you with this book here. You can see that page here, that this is public road administration. Public Road Administration Classification System for Soil. This is 1945, not today. Means it's 75 years old. 75 years before it was done. And in this is general classification, group classification, group classification, sieve analysis, and then there is percent policy, and then there is characteristic of friction, and then group index, and usual type of significant constituent materials, and general rating as subgroup. So 1, 2, 3, 4, 5, 6. Okay, that's 6, not 7. Well, let us see how it works. Grain classification is group classification. In grain classification there are two areas. One is granular materials, that is 35% or less, passing 75 micron ISC, and silty clay material more than 35%, passing number 200 C. So 35% it passes through 75 micron IS. See, it is granular material, and silty clay material is more than 35%, passing number 200 is called siltic clay. So we have this formula here. So you understand granular and siltate. Now group classification. This was general classification. Now group classification. Now group classification is you can say A1, A2, A1, A2, A3, A4, A5, A6, A7, A7-5, A7-6. In A1, it's A1A, A1B, A3, A2, A2-4, A2-5-6, A2-7, and A2-7. In siltic clay is A4, A5, A6, A7, A7-5-5. Now, nothing is given here about that, we have only numbers. So, below A1 is given A1A, A1B, below A3 is 51, no, let's leave it, nothing in that. Then A2 is A2-4, A2-5, A2-6, A2-7, that is within granular materials, and in silty materials A4, A5, A6, A7, A7-5, A7-6, and it looks a kind of mix-up of various soils, not exactly separated one. There's group clarification. I will tell you what's the group. Now sieve analysis is saying something else. What is saying sieve analysis? See, in sieve analysis, percent passing. 2 mm IS sieve, 425 micron sieve, and 75 micron IS sieve. Now it says 2 mm IS sieve. We consider 2 mm IS sieve, then 425 micron sieve, and 75 micron gas. We are talking of public administration system. In sieve analysis, 2 mm IS sieve and group A1, 50 mm max, 50 max, that's below A1A. Passing 2 mm sieve in IS sieve is 56 mm maximum, and 425 micron sieve 30. .425 micron sieve 30 maximum in A1A and 51 maximum. And 75 micron sieve is 13 maximum. Now is two numbers here is A1, and in A1 there are A1A and A1B, and again 52 mm sieve is 50 maximum, and that is classification of group is, and 425 microns 30 maximum, and 51 maximum A1B, and it's 13 max and 25 max. A3 in 425 microns it is 51 mm minimum and in 75 microns 35 max. Then you go further, A3 is for 51 minimum and 10 maximum. In 51 is in 425 micron, while 75 micron. ASC this is 10. Then you go to group A2 and in the A24, 75 micron ISC is 35 max, and A25 this is 35 max, and A26 is then in A2 it's only 75 micron seal, where 35 max and 35 max and 35 max and 35 max. And then in A4, A5, A6, A7, A7, 5, 6, 6 is safety material area 36 or 36. Now come on to, I repeat again, come on to characteristics of friction passing 425 maximum seal limit, plasticity index. Liquid limit and plasticity index. These are very important. Get this way. Yes, it's better. Get this way. Liquid limit says liquid limit in group A1, plasticity index is 6 maximum. That is characteristics of friction passing 425 micron seal. Plasticity index is 6 maximum. In group A3 it's NP, and non-plastic I mean to say. When you say NP means non-plastic. And in your, this is friction passing 425. So then it is A2 group. Liquid limit is 40 maximum in liquid, and A2 and A24, while plasticity index is 10 maximum. 10 maximum here, this increases, that is in group A2, in A24. In A25, this is liquid limit is 41 minimum and plasticity index is 10 maximum. Then in A26, liquid limit is 40 maximum and plasticity index is 11 minimum. 11. And same is A27. A27, plasticity limit 40, 41. That is 41 and plasticity index is 11 minimum. If you go to silt content materials, silt clay materials, this is more than 35% passing through 200, and in this granular it was 35% or less passing 75 micron. Here is 200 in number, more than 35 passing number through In this case, groups are A4, A5, A6, and then A7, A7, 5, and 6. What it says? It says in this case, in characteristics of friction passing 425 micron, and then this is liquid limit is there. So it is 40 maximum for A4, 40 maximum liquid limit, and elasticity index is 10 maximum. Then it is 41 minutes in A6 and 10 maximum for elasticity index. These are very important numbers. And then A6 is 40 minutes and 11 minimum, and next last is this A7, A7, 5, A6. Now, little patience we have to keep in this, because these are data and very important data. Not that we are I'm just reading. If you go to group index, it's A1. This is 0, A3 is 0, and A2 is 0, and then A26 and A27 maximum, and that's 4 max, you can say. Then you go to group A4, A5, A6, and A7, A75, A76. It is 8 max, 12 max, 16 max, 20 max respectively. Usual type of significant constituent materials. In this A1, stone fragments, gravel and sand. And if you go to A2, all these 4, silty or clay, gravel or sand. And then A3 is fine sand. And then go to A4, A5 with silty soils, and A6 and A7, 7, 5, and 6 is clay soil. In written below group A2, A3, yeah, this is excellently good. Excellent good, that is in this one, and this is silty clay area, fair to poor. Once again I show you this table here, table form. That these are talking here. You see, these groups are written here. And there are various we will re-explain this because it's a little tedious. Now we go to another one. Now, no negative value of A, B, C, D are to be taken. There's something else is here. Sorry about that. So no negative values of A, B, C, D are taken in case any index value is less than lower limit for it under A, B, C. So no negative values of A, B, C, D are to be taken in case any subject, any value is less than lower limit for it under A, B, C or D, then corresponding value of constant is taken as 0. Complete classification system is shown in table 14.3. Classification is done according to following procedures. Now we are talking of that table. It's simple, it's not for just the 4 lines. Find out liquid limit and plastic limit and do sieves analysis. So find out liquid limit and plastic limit and do sieve analysis. With this data, proceed from left to right in table 14.3. Eliminate groups in which data do not fit in. A proper group for soil will be first group from left into which data fits in. 4. Take plasticity indices as under for splitting A7 groups into subgroups of A75, A76. Now plasticity index equal to A minus 7. Alright, now it says take plasticity index as under for splitting A7 group into subgroup A75, A76. Plasticity index equal to A75 less than equal to liquid limit minus 30 and plasticity index A76 equal to liquid limit minus 30. This is just explanation of this, further explanation. Unified soil classification. Unified soil classification, that is. So, Mr. A. Casagrande, as we developed before also, developed the soil classification system which was adopted by US Corps of Engineers in 1942. Was named as airfield classification. Airfield classification. Later, Mr. Casagrande reviewed classification system and was adopted by US Corps of Engineers and US Bureau of Reclamation in 1952. This was known as Unified Soil Classification System. And this system could be used not only once. Unified soil classification. We are talking about this one. 1952, Bureau of Reclamation in 1952. This was known as Unified Soil Classification System, and this system can be used not only for airfields but also for foundations classification system, and are divided foundations, embankments and other engineering features. So soil under this classification systems are divided into two categories: fire category and first category. I think I am making some mistakes. excuse me for that. First category, coarse grained soils with material passing 75 micron ISC up to 50%. That is coarse grained soil. Other is second category, fine grained soil with material passing 75 micron SCO, more than 50% in organic soils. So up to 50% in 75 micron, it is passing more than, I can say, up to 50%, and in case of fine grained soil, more than 50%. That's called first category. It's called second category. Main distinction between both categories is degree of plasticity. Let's go. Main distinction between both categories, degree of plasticity. Degree of plasticity. Now, coarse grained soils, each soil components has been assigned a symbol. This is, we say, G, then S, then W, then C, then P. G is gravel and gravelly soil. G stands for gravel and gravelly soil, and S stands for sandy soil. S stands for sandy soil. Both groups have further been subdivided into 4 groups depending upon grading, and that is W, C, P. W says well graded clean, well graded clean. C says well graded with excellent clay binder. Then P is poor graded fairly clean. So WCF, well graded. So W is well graded soil, well graded clean, and C is well graded with excellent clay binder, and P stands for poorly graded fairly clean. And this is alright. Now S sand, G gravel, W well graded, C well graded with excellent clay binder, and alright, now we go for these lattice symbols in different combinations, name type or coarse grained soils. For example, GC means clay gravel, now we go further down, fine graded soil. Just let me see some vision I was seeing in this soil. Yawning, yeah, I don't know why. After this, there's another classification, and that's very important from our point of view. That's called Indian Standard Classification, and that's some more. Now, we say M. This fine-grained soils. Fine-grained soils have been assigned following symbols. We actually read the other one, that is coarse-grained soils. G, S, gravel sands, sound. Now, in this fine-grained soil, this MCOPT and LJH. These are symbols. What does M stand for? M stands for what? Inorganic salts and very fine sand. C is inorganic clay, O is organic silt, and clay is an organic mat. Peat is peat. Then the fine-grained soils have been further subdivided according to liquid limit, which is a good index of compressibility. So you can say liquid limit below 35 indicating low compressibility. This is what's happening today, I don't know. Something wrong somewhere. 90% humidity. Now it's saying liquid limit below 35, that's L is liquid limit in fine grained soil, 35 indicating low compressibility. Liquid limit J between 35 and 15, this indicates medium compressibility. And H, liquid limit above 50, indicates high compressibility. So up to 35 is compressibility, you can say low, indicating low compressibility, and then 35 to 50, this is medium compressibility, and H is high compressibility. 35 to 50 is medium, and this is above 50 is in the high compressibility. So combinations of these symbols indicate name of fine-grained soils. Combinations of these symbols indicate name of fine-grained soils. For example, ML means inorganic silt. Combinations of these symbols indicate names of fine-grained soils. For example, ML means inorganic silt, and with low to medium compressibility. Now, grain size distribution curve of the soil can give a fairly good idea whether soil is poorly graded or well graded. size distribution occurs in grain size distribution curve of the soil can be fairly good. So it says grain size distribution curve of the soil can give a fairly good idea whether soil is poorly graded or well graded. This can be done by finding coefficient of uniformity and coefficient of variance. Coefficient of uniformity, how to find? Let us say uniformity coefficient is D60 over D10. And coefficient of curvature of transportation. Now, what is coefficient of our D60 and D10, D30, etc. You see this 60 and D10? Now this 60, 10, 30, etc. These represent size of particles against those something more. So D60, D10, D30 represent size of particle against these percentages on a grain size distribution curve. Coefficient of uniformity should be more than 4 for well graded and more than 6 for well graded sand. For well graded soil, grade 7 sand. And says that, let me see, this size that represents here is D60, D10, D30. So these 60 etc. 10 30 represent size of particle against these equations. Size of particles against these percentages on grain size distribution curve. Coefficient of uniformity should be more than 4. Coefficient of U, value of U, should be more than 4 for a well graded and more than 6 for a well graded sand. For a well graded soil, gravel, sand and mixtures. So what says there's a limit here, it says 4, coefficient 4 is used, more than 4, coefficient of uniformity should be more than 4 for well graded and more than 6 for a well graded sand. So for the well graded, this should be fine sand, fine clay and should be more than sand. For gravel, for well graded soil, gravel, sand and mixture, value of coefficient of curvature should be between 1 and 3. Maybe this D60, D10 very tough, I just informed you that one. We missed that point. Maybe you may question that why you're taking this. That's the point we'll miss. Okay, we'll find that somewhere else. Now it says soil groups of ununified classiform. Soil group of unified classification system and their important properties have been given in table 14.4. 14.4 IS 1498 1959 is IS. Describe Indian standard on classification of soil for general engineering purpose. Soils have been divided in various areas. Okay, I will continue, no problem holding. Why hold? I can't hold it like this. I have no problem time. If I don't continue, I forget it. So as a first of all, see this table here, table 14.4. Table 14.4. Well, this must be available in code, but I am not showing code at the moment. I'm just showing book. So I forget code, And also I will show you something else which I forgot before that. Actually, the book is not in sequence, that's some problem. But I don't mind that. One should be having that much capacity to get in quickly to required portion. Yes, it is here. Uniformity of coefficients. Uniformity of coefficient U that I was talking of. Here there was a question. A uniformity coefficient is equal to U equal to D60 over D10. D60 is the maximum diameter of smallest 60% by weight, and D10 is the maximum diameter of the smallest 10% by weight. D10 is sometimes called effective size or effective diameter of soil sample. And for uniformly graded soil, value of U is unity. Value of U is unity. When soil is very uniform, U is less than 5. But it is of medium uniform U, it's of medium uniformity U, lies between 5 and 15. When soil is very non-uniform, this is U is greater than 15. Right? It's a very important formation. I am saying D60 over D10 equal to U uniformity coefficient. Now it says coefficient, this is defined, okay. Degree of uniformity is very important in case of coarse-grained soils. Degree of uniformity can be expressed in form of number by coefficient of uniformity. More uniform a soil is, steeper will be the curve. More non-uniform a soil is, flatter is curve. So where is that uniformity coming from? That's fine to understand that. This is here, this is this chart diagram here. This is soil mechanics. Okay, that's okay, fine. Particle size distribution curve shows many features of soil. Curve will be clearly indicate whether soil is coarse-grained or fine-grained, and its value show that soil is uniformly graded over particle size distribution shows many features of soil. A curve will clearly indicate whether soil is coarse-grained or fine-grained. It also shows whether soil is uniformly graded over entire range of particle size. Such soils are well-graded soils. Well-graded soils contain particles of all sizes. If a soil is deficient in particle size of grading, curve becomes flat at that stage. Now this is a grain size distribution diameter, and here is percent fine by weight. This curve has been drawn with percentage finer by weight and as coordinate and particle diameter D in mm as abscissa. Particle diameter has been put on the scale. So let's show you this. This is that curve. Important curve, you know. This is that one. I was just explaining you what, and then I will later on discuss with this. So its classification is, it says this 60 is maximum diameter of smallest, 60% by weight is this 60, and 10 is, this is maximum diameter of smaller 10% by weight. So D60 data. Now for uniformly graded soils, value U is unity. Value uniformly graded soil. When soil is very uniform, U is less than 5. Medium uniformity is U. So that's what we say. So means if you say that when soil is very uniform, it is used less than 5, and but it's a medium uniformity, this is utilized between 5 and 15. Soil is very non-uniform, so it goes on increasing if soil is not uniform. If uniformly graded soil, use unity. So in the case of use unity means smaller particle and bigger particle have no meaning. Both are equal, so it's unity. When you say in this case that 10%, you say D60 is maximum diameter of smallest 60% by weight, and D10 is maximum diameter of smaller 10% by weight. So you say unity, both equal, and when say one is say ratio 15 means let's say D16 15 and that's 10. Okay, let's go a little further now. We'll take up this later on because it's not. Now we are talking of this Indian standard. We'll come on back. First says, as we said, coarse-grained soils. Coarse-grained soils, more than 50% of which is higher than 75 micron ISO. Coarse-grained soils, more than 50% of which is bigger than 75 micron ISO. Fine-grained inorganic soils, more than 50% of which is smaller than 75 micron ISO. Silt and clay organic. Then silt and clay with organic content and peat. Let's do this way now. This is table 44. In this is table 44. There are now 7 columns in this. Group symbol, typical name, value of embankment, permeability centimeter per second, compaction characteristics, unit dry weight gram per centimeter square, value for foundation. Let me show you this again better. You can see that 7 columns here. And these are again I am telling you column number 1, group symbol, column number 2, typical name, column number 3, value of embankment, column number 4, permeability centimeter per second, and compaction. On number 5 is compaction characteristics, and 6 is unit dry weight gram per centimeter square, value for foundation is 7. And how many pages in this? Let me see. 1, 2, 3, 4. Okay, not much. So in this is now let's start in group symbol 1. What it says? GW. It is GW. So GW, this is now typical name is this group symbol GW. Well graded gravel. Sorry, it fell because thick. Let me keep it here. Yeah, keep it here. Let us see what happens. How my scanning status? Let us see. Still there's time for scanning status. No problem. It's time. What I say, well-graded gravel, sand mixture, little or no fines. This group is GW. Valuation of embankment, very stable, very stable, pervious shells of dikes and domes. Then permeability, centimeter per second, is K. Permeability is equal by K. K is greater than 10 to the power minus 100. What is mean? 10 to the power minus 2 is K equal to this. K is greater than 10 to the power minus 2. 10 to the power minus 2 is 1 over 100. So K is greater than 10 to the power minus 2. This permeability coefficient. Compaction characteristics 5. Good tractor rubber tired street wheel rollers. This compaction characteristics, good tractor tired rubber tired straight wheel roller. Unit dry weight gram per centimeter square 2 to 2.16. Value for foundation good bearing value. Then it's so heavy. Yeah, but my hand can't hold it. See, that's a problem. I can't hold it. You are kept like this. No space to hold it. If you taught here what to do, I can't help it, I can't help. I don't have a big desk here. So if I keep off, you can't listen to me. I don't have earphone. Well, value for foundation, good bearing value. So I read it again. This is GW. This is a group symbol. Typical name is well-graded gravel, sand mixture, little or no fines. Its value of embankment is very stable, pervious shells of dikes and dams, and permeability centimeter per second is K is greater than 10 to the power minus 3. And compaction characters, good tractor, rubber tired, straight filled rubber, and unit weight then unit weight is 2 into 10 to the power minus 6. We go to number 2, that is GP. Class is group symbol is GP. Poorly graded, P stands for poorly graded gravel, or gravel sand, or mixtures little or no fines. And goes to value of embankment. Reasonably stable, pervious shells of dike and dams. Then value of embankment, reasonably stable, pervious. Hold on. We have to understand this. It says reasonably stable, pervious wheels of dikes and dams. Permeability centimeter per second, K is greater than 10 to the minus 3. Compaction characteristics, same as above. So you can say compaction characteristics as for GW, good, tractor, rubber tired, street, wheeled roller, and K is same. Then duty, unit duty there. And the next is its dry weight per and then to 1.8422 gram per centimeter square, good bearing value. GB is not very good according to property, but then GM group, the GM group is silty gravel, poorly graded gravel, sand, silt mixture, reasonably stable, unsuitable for shells but suitable for impervious core. Now its permeability is K is greater than 10 to the power minus 3. In that case, it is good bearing value. Now third is GM. Sorry, not GM. GC. Fourth is GC. Clay gravels, gravelly sand, little or no fines. So one by one it's better to understand. GC is clay gravel, C clay gravel is G. So when we say number one was GW, it was W stands for well graded gravel. Then we say GB is poorly graded gravel. GM was silty gravel, poorly graded. Now GC is clay gravel, C stands for clay possibly, clay gravel, gravelly sand, little or no fines. Now it is number 4 and GC, and this is fairly stable, used for impervious core. So this is impervious core, I think. This is number 1, which is impervious. No, number 2. Previous also GM was impervious. Suitable useful for impervious core, and that is clay gravel. Because of clay, water cannot pass through. And permeability is 10 to the power minus 6. You see, in first one was 10 to the power minus 2. In second one, GP was 10 to the power minus 2. In GM it was gate, permeability is greater than 10 to the power minus 3 to minus 6. This means they increase something, some subs. Okay, now GC we are talking. It's now just like GM. K reduced from T to 10 to power minus 3 to 30. Sorry, 10 to power minus 6. Here is further gone up. 10 to power minus 6 to 10 to power minus 8 because of silt. This changed its value from values of k greater than 10 to power minus 3. Now it's in because of because of silt in that case. 10 to power minus 3 to 10 to power minus 6 here for permeability. And now here because clay is there, this case of the coefficient of permeability equal to 10 to the power minus 6 means further reduced to 10 to the power minus 8. See, 10 to the power minus 6 to 10 to the power minus 8 means million to, if you say in positive unit, 1 over million to 1 over 10 millions, or you can say crores, 10 crores. What crores here in Arabic, you can say that. So then its compaction characters is fair rubber tied shape foot roller and unit dry when dry unit weight dry. This is 1.84 and 2.08. Then its value of foundation is very is a good. Yes, now we go to next one, and that is SW, not GW, SW. Well graded sand, assistant was sand, gravelly sands, little or no fines. Value of embankment very stable, pervious because of sand. Sections slope protection necessary. Here permeability is 10 to power minus 3. Means not like that it was 10 to power 8 now. It is compaction, means compaction is good and use tractor. And unit dry weight is 1.75 to 2.08 gram per centimeter square. That is unit dry weight, and value up to and you can say its weight here known 1.76 to 2.08. Good bearing value. So these are 1, 2, 3, 4, 5 groups on this page, and then there's another 1, 2, 3, 4, 5, 6 on other page. 1, 2, 3, 4, 5, 6, 7 a page. So and then so we say here I repeat this first so that I have to come to this page again. I repeat, we are studying on this page group symbols GW, GP, GM, GC, SW, and GW stands for well graded gravel sand mixture, little or no fines. I'm just trying to tell you just to how to read this so you understand meaning directly. And this is well graded gravel sand mixture, little or no fines. Value of embankment is very stable. Why? It is stable because of gravel sand mixtures. It's stable, and because it is gravel and sand, this means there is porosity, pervious shells. Water is permitted to flow in, and of dikes and dams, and its permeability centimeter per second is 10 to power minus 2, and compensation and compaction is good. By tractor we can do it, rubber tire we can use, and wheel rollers, rubber tire wheel rollers we can use, and unit dry weight of this is 2 to 2.16, that is tons per unit dry weight gram per centimeter square to 2.16, and value for foundation is good bearing value. This is number 1, and this is GW, well graded gravel, and this is GP, this is poorly graded gravel and or gravel, sand or mixture, little or no fines, and it says its value of element means because there is gravel and silt is little bit dangerous, so you can say that this is poorly graded gravel or gravel, sand or mixtures. Reasonably stable means not very stable, reasonably stable because of gravel and pervious shells or dikes and dams. Then K permeability is greater than same 10 to power minus 2, and compaction is same, good tractor, rubber tired, straight wheeled roller, and unit dry gram weight per gram per centimeter square, and that is 1.8422. Also value of foundation is good. After that, its unit dry weight is 1.8422 and good bearing value. Now go to GM, silty gravel, poorly graded gravel, sand, silt mixture, reasonably stable, unsuitable for shells but suitable for impervious core. So it is impervious core means permeability is reduced, that's why it's impervious. K has gone from 10 to power minus 3 to 10 to power minus 6. So good with, we say, compaction, good with class control, rubber. With a close control, rubber tired, shape for killers. Next, then you can say some good with close rubber tires, close controller, shape controller, and 1.9 to 2.16, and good bearing value. So its compaction is good with close control, rubber tired, sheep foot roller. Now GC, next one. Then you come to GC. GC, that is clay gravel, clay gravel, gravelly sand, see little or no fines. Here is indication of, you say, clay is there. This means, you know what I mean, permeability is reduced. This means fairly stable, useful for impervious core. Strength is less because of silt, clay, but impervious increasing property of, well, K is increased 10 to the power minus 6 to 10 to the power minus 3 means impervious character works here. Fair rubber tire shape foot roller, and 1.84 to 2.08, good bearing value. Then SW, well graded sand, gravel made. Here you can say then, I can say we can go further. You say fair rubber tired and 1.8 for this and good bearing. Well then SW well graded sand, gravelly sand. Is there also here no clay and nothing, and no that also very stable, pervious. Here there is no clay, it's pervious. So simple. Slope protection necessary. Slope protection necessary. So K is greater than 10-3. Good tractor 1.75208. Good bearing value. So this was the first page. I'll go to second page. I'll try to finish it in today's discussion because this is our specifications. Now go to SP, that is there's SP, SM, BC, and SC, ML, CL1. Let's take watch. See, we have to think and understand. This means where there's clay coming in, your find coefficient of permeability is much reduced. And but you see, it's used as impervious layer. Now SP, so same thing here of the same number of columns as we said. So now I say, I will not take all those. I say SP poorly graded sands or gravelly sands, little or no fines, and reasonably stable, useful for dike section with flat slope. Good, and this is K is greater than 10 to power minus 2. So this is 1. This is a good tractor 1.6 to 1.92, good to poor bearing value depending on density. Okay, so that one. Next is SM. Silty sand, silt has come in here. Silty sand, poorly graded sand silt mixture. Fairly stable, useful for impervious cores or dikes only, and K is greater than 10 to power minus 3 to 10 to power minus 6. Good with close control rubber tired sheet food roller. .76 and 1. It's come down to 1. Silt sand, polygable sand, and good to poor bearing value depending on quality. Then is SC, clay sand. Clay sands, poorly graded sand and clay mixture. Because clay is there, let us see what happens. Clay sands, poorly graded sand, clay mixture, fairly stable, useful for impervious cores for flood structures. K is greater than 10 to the power minus 4 or to 10 to the power minus 8. Further change, permeability further reduced, fair sheep, fair sleeve foot, roller, rubber tired rolls, 1.68 to 1, good to poor bearing. ML, inorganic silt and very fine sand, Inorganic silts and very fine sands, silty or ML, ML, inorganic silt, inorganic silt, that is, and very fine sand, silty or clay fine sand or clay silt with none to low plasticity, poor stability, can be used for embankment, K is 10 to power minus 3 to 10 to power minus 6, good with close control essential, sheep foot roller, rubber tired roller, 1.52 to 1.92. Very poor, it says, very poor system to the perfection. So this is the division that we have. So we have gone through ML, now CL, inorganic clay, CL, inorganic clay, and gravelly clay, inorganic clay, gravelly clay, sandy clay, silty clay, lean clays of low plasticity, stable, impervious, coarse, and blanket. What's this big one again? 10 to power minus 6 to 10 to power minus 8. So it is now here, we can say 10 to power minus 6 to 10 to power minus 8, fair to good, sheep foot roller, rubber tired, 1.52 to 1.96, it's going down weight-wise, and good to poor bearing. OL, organic silt of low plasticity, not suitable for embankment, K is 10 to the power minus 4 to 10 to the power minus 6. Fair to poor as sheet foot roller, 1.28 to 1.6. Good to poor bearing. Now I say OL, organic silt of low plasticity, not suitable for amendment. K is 10 to the power minus 4 to 10 to the power minus 6, fair to poor, sheet foot roller, 1.28, 1.6 means further down, and good to poor bearing. This is second page of this. So we have gone through SP, SM, SC, ML, CLT, and even here, permeability coefficient has gone to that level. You see, even in one case it is gone to 10 to the power minus 6 to 10 to the power minus 8. Means where is the client's help test question is coming in. Now next page is there, and I wanted to actually take some time on that. That's why I was a little slow. It should be understood first. Running fine. So in this case, MI, CI, OI, MH, CH, OH, PT. Let's see. Inorganic silt, silty or clay fine sand, or clay silt of medium plasticity. What it says in number 3, conditions means what it says on column 3, same. you can say purpose actually. Its characters, its quality, what it says here in this page was number 3. Title was here nature value of embankment, value of embankment. So this is same, and also number 4, that is K value, and number 5 is number 5 here again I'm telling you it is compaction character, so it has gone same way. So 6 and 7, okay, we go on like this. So this inorganic ML, inorganic silty or clay, fine sand of clay, silt of medium plasticity. So it says that K value as, and as means previous K value is K is 10 to power minus 4 to 10 to power minus 6, and it's before it says not suitable for embankment. So it's not suitable for embankment in all these cases, 3 cases, and K value is this fair to poor sheet foot roller, and also here fair to poor, and number 6 is blank, number 7 is blank, it's not given here, so it's not even written, so I can't say that. So number CI is now, CI is inorganic clays, gravelly clays, sandy clays, silty clays, lean clays of medium plasticity. So all same as above, which was not suitable for embankment. K is 10 to power minus 4 to 10 to power minus 6, fair to poor sheet foot roller, and no further. Then you can say again OI, organic silt and organic silty clays of medium plasticity, and it is same. This means not suitable for embankment. K is 10 to power minus 4 to 10 to power minus 6, and this is fair to poor sheet foot roller, and then it says nothing else. Now it says in this case poor to various sector ML, CL, DL, it says same one. Now we go to MH. Actually in this case, my case it says ML. Here in this case of fair to poor it says ML, and ML is good with close. What I'm saying when I said MI, and it says its use as case number 5. Number 5 here is fair to poor sheet foot roller. So it's number 5 here. MI, CI is CL, and CL is fair to good sheet foot roller rubber tired, and then it says OI is OL, and OL is fair to poor sheet foot roller. Now we go to MH. MH, inorganic silt of high compressibility. Inorganic silt of high compressibility. This is analytical study in soil mechanics to understand that. So it says poor stability, core of hydraulic fill dam only. Hydraulic fill dam only. K is greater than 10 to power minus 4 to 10 to power minus 6 because of inorganic silt. Poor to very poor sheet foot roller 1.12 to 1.5 to very little. Poor bearing. CH next is CH, inorganic clay of high plasticity, fat clays. Poor stability with flat slopes, thin cores, blanket and dike sections. K equal to 10 to power minus 6 to 10 to power minus 8. Fail to poor sheet foot roller 1.2 to 1.68. Fail to poor bearing. OH, organic of medium or high plasticity, not suitable for embankment. K is equal to 10 to power minus 6 to 10 to power minus 8. Poor to very poor sheet foot roller 1.05 to 1.6, very poor bearing. PT, peat and other highly organic soils with very high compressibility, not used for construction. K is not given. Compaction not practically possible. And remove from foundation bad peat. So in this we are list on the page Mi, Ci, Y, Mh, Ch, OH, peat. Mi is inorganic silt, silty or clay, fine sand or clay silt of medium plasticity. And then Ci is inorganic clays, gravelly clays, sandy clays, silty clays, lean clays of medium plasticity. OI is organic silts and organic silty clays of medium plasticity. In all these cases, it is not suitable for amendment, and it is K is 10 to the power minus 4, 10 to the power minus 6, and this is one is ml. ml is good with close control essential sheep foot roller, rubber tire roller. Other one is Ci is Cl, and Cl is fair to good sheep foot roller, rubber tire, and other one OI is OL. OL is fair to poor sheep foot roller. Then we go to MH, which is inorganic silt of high compressibility, poor stability, core of hydraulic fill dam only. K is greater than 10 to the power minus 4 to the power minus 6. Poor to very poor, sheep foot roller 1.1 to 1.52. Poor bearing, NCH, inorganic clays of high plasticity for clays, poor stability with flat slopes, thin cores, blanket and dike sections. K equal 10 to the power minus 6 to 10 to the power minus 8. Fair to poor sheep foot roller 1.2 to 1.68. Fair to poor bearing. And then OH, organic of medium or high plasticity, not suitable for embankment, and K is equal 10 to the power minus 6 to 10 to the power minus 8. Poor to very poor, sheep foot roller 1.04, 1.6, very poor bearing. And PT, peat and other highly organic soils with very high compressibility, not used for construction. No K, compaction and practically not possible, and no value of density or weight, and remove from foundation. So we have gone through these 3 pages of Indian Act. Now you understand very well what is Indian classification system. It's little detailed but based on something else. It's again something else here, and this Indian soil classification 1498 to 1498, year 1959. This is IS 1498, describes Indian standard on classification of soil for general engineering purposes. In this system, soils have been divided into 4 categories. Coarse grained soils, more than 50% of which is bigger than 75 microns, IS. See, fine grained inorganic soils, more than 50% of which is smaller than 75 microns, ISC, and silt and clay with organic content, and peat. So these are 3, and we have gone through all these. I can say 5 items on one page, and you can say about 6 items on the page, 5, 6, 11. Then there is 3 and 7, 11, 7, 18. 18 items are there. We studied here. Now, what it says, let's go, that symbols have been loved. These symbols have been given in, and these are classifications of coarse grained and fine grained soils, very similar to unified system of classification. Fine grained soils are classified on basis of liquid limit. Fine grained soils are classified on basis of liquid limit, WL. Now symbol is, let us say, G, it says gravel, S, sand, M, silt, C, clay, O, organic silts and clay, PT, peat, W, well graded coarse grained soil with little or no fines. Again, because this is important here, again I say G is gravel, S is sand, G is gravel, S is sand, M is silt, C is clay, O is organic silts and clays, PT is peat, W is well graded coarse grained soil with little or no fines. B is well graded coarse grained soil. B stands for well graded coarse grained soils with clay binder. P is poorly graded coarse grained soil with little or no fines. And L is fine grained soils with low compressibility, having liquid limit from 0 to 35. I is fine grained soils with medium compressibility, having liquid limit from 35 to 50. H is fine grained soils with high compressibility, having liquid limit more than 50. Here you have to remember something. That's the example B, which says wet, well graded, coarse grained soil with clay binder. So you can say binder is here B. This means no single binder stands for this. Well graded coarse grained soils with clay binder. So clay binder is important here. That's why B is given. P is poor graded. P is poor. P stands for poor. Poorly graded coarse grained soils with little or no fines. Then L is means limit, I think, liquid limit. Fine grained soils with low compressibility, or low compressibility can be with having liquid limit 0 to 35. Then I is, let's see what's that. Fine grained soils with medium compressibility, having liquid limit from 35. This is the intermediate. You can say this is H is fine grained soils with high compressibility, having limit for this. So this is compressibility here. L low compressibility, and that's related to I is intermediate compressibility, you can say, and H is high compressibility. So these are linked to compressibility. L, I, H. One is B stands for binder, P stands for poorly. These are characters of these. So this is, L is low compressibility, means liquid limit 0 to 35, and I is intermediate compressibility 35, liquid limit 35 to 50, and H is high compressibility where liquid limit is more than 50, and LSI classification has been given. Now we have gone through the article already. Now features in ice class what says is, now we'll read that. It's one. No issue. We're saying, number one, classification is based, this I'm talking of characteristics, features of IS classification. Classification is based upon physical properties of soil, not chemical properties, physical properties of soil. System divides soil in 4 major divisions and 18 subdivisions, each having different characteristics. This system gives 5 field identifications tests, namely visual, examination, wet and manipulated strength test, thread test, dilatancy test, and dry strength test. So how many tests? Visual examination, wet and manipulated strength test, thread test, dilatancy test, and dry strength test. It gives general properties of soil. Which has strength in natural state. It gives general properties of soil. I'm saying general properties of soil such as strength in natural state, strength when when strength with remolded and wet, etc. It gives relative suitability of soils for general engineering purposes. ISI does not specify numerical limits of value of coefficient of uniformity or I repeat this 5 again because this is Indian standard and many of you have to deal with this. Classification based upon physical properties of soil. Physical properties means number 2 is system divides the whole. The system divides soils in 4 major divisions and 18 subdivisions, each having different characteristics. The system gives 5 field identifications tests, namely number 1 test is visual examination, number 2 test is wet and manipulated strength, and number 3 test is thread test, and number 4 is reluctancy test, and then dry strength test. It gives general properties of soil such as strength in natural state, strength when remolded and wet started. And also it gives relative suitability of soils for general engineering purposes. ISI does not specify when numerical limits of value of coefficient of uniformity or coefficient of curvature for making distinction between a well-graded soil and poorly graded soil. This is basics of that. Now we go to this. It means the soil structure as we studied today. Before. I just means after the start soil structure. This is a classification of soils. Basically, soil is collection of mineral particles. This is the definition of that. Soil is collection of mineral particles. It's collection of mineral particles which are interspersed with voids. Interspersed with voids. Void spaces may contain air or water or combination of both. Soil structure is pattern of arrangement of individual particles or of aggregation and combination of different particles in a soil mass. Soil structure is very important factor because number of engineering properties such as permeability, compressibility, shear strength, etc. are affected by structure. Affected by structure. Normally there are following types of soil structure. We have already gone through them and they will repeat that also. And these are single grain structure, honeycomb structure, flocculent structure, dispersed structure, coarse grained structure, skeleton, cohesive matrix. We have gone through them, and if you want to see back again, I can show that again. Yeah, we have gone through that. These are different ones, and no problem. Maybe just refreshing something. And this is here you can say grading of structures. Names of those that I'm talking of here. Single, you can say these are, again I'm saying single grains, honeycomb, flocculent, dispersed, coarse grain and cohesive. And this is other one, which is a very important point, flocculent and dispersed structure, which is common. Flocculent is this side and dispersed is that side, particularly for clay. And which is this one, and of course this is and then And he also we discussed kelonite group and micromalonite group and elite group and permalite group, and we'll just see a look on that. As we said here, these are different gradations of that, and that is where here, so I can say is this, this is our symbol here. This is octahedral, and again here you can say these are groups: kelonite, montmorillonite, illite, vermiculite, and these are different. Yeah, octahedral is rectangle, one is tetrahedral, other one is octahedral, and these rectangles are called gypsite, and this is a combination of both, like that. As you go again, you will find different one here in this case, and here is this various this like books pages, and here also 10, and this measure in angstrom units. All this we discussed, and we will discuss later also for refreshing, because this is kelonite mineral is stacking of such 7 angstroms, and 1 angstrom is 10 to the power minus 7 millimeter. 1 angstrom is ANGSTROM, angstrom is 10 to the power minus 7 millimeter, and kelonite mineral is stacking of such 7 angstrom thick shades, and then structure of is the mantle, and then there's a 10 angstrom also, other one that is 10 angstrom, and that is your montmorillonite, figure 14.11, which is there, and it's there already shown, and that is unit is 10 to power, that's at I mean to say 10 angstrom. One from that, the one is 7 angstrom, is that's kelonite, and kelonite mineral is a stacking of such 7 angstrom thick shades, whereas this 10 angstrom is thickness of each. Montmorillonite group is that 10 angstrom, much more water can be there, like that. I already explained, we'll keep explaining later also, because it's very important. These are very important parts to understand in soil. You need just to understand basics of that. And we have capillarity and permeability. This is here. Capillarity, permeability, well means what capillarity and permeability is. And we'll see if we can, means I confine to theories of this, not numericals. Numericals you can do yourself if you understand that. It's not a big issue, it's no problem. And seepage forces and flow nets also very important. We'll see how it works, and I'm not seeing here, I can say that's for dams, and for that compaction, we also discuss compaction is a very important point, and compaction is the expulsion of void, reduction of voids, and consolidation is leads to consolidation and long time, and but it takes a lot of time for compaction. There are two different studies, you can say. In compaction itself, because of how does compaction and consolidation are different words. It takes a lot of sheer strength of soil. We'll discuss others. So means I just want to concentrate on something that's very important for this. Not just much of that, but refreshing is important for everything. Refreshing study is never stability of slopes, and it's all geometrical patterns here, nothing to do with this now. I'm just trying to pavement designs, of course CBR is important here, and we'll take up that as well. Then soil stabilization, as we discussed, mechanical stabilization, and there was this stabilization, soil stabilization we discussed that day. Is alteration to any property. Soil stabilization is alteration of property of the soil, to improve engineering performance. There was a soil stabilization is alteration of its property to improve its engineering performance, and it's only one of many methods available to soil engineer, and this technique is adopted only after a comparison with other technique. Buildings, dams, roads, airports, etc., rest upon soil, and many of these structures also employ soil in their construction. And to obtain a soil at a particular site which is most satisfactory for a particular use as it exists is ideal. But in most of cases, this is not possible. Following are various methods which are adopted to deal with unsatisfactory soils, and that is bypass poor soil, you can say bypass poor soil. Bearing piles are used to carry a bridge load through weak soils to a firm soil below, firm strata below. Highway alignment can be changed to avoid a swamp rather than try to transverse it. Then second is remove poor soil. Poor soil like peat is sometimes removed from site and replaced with good soil. Redesign structure. Whole structure and its foundation may be redesigned to account for poor bearing capacity of underlying soil, or treatment of soil to improve properties. This is known as soil stabilization and has been dealt in detail in here. Soil stabilization used for following purposes: to increase or decrease strength or reduce sensitivity of strength to environmental changes, especially moisture changes; to increase or decrease permeability; to reduce compressibility. So let us see what is that. Soil stabilization used for following purpose. Purpose number one is increase or decrease strength. However, I don't understand decrease here. Increase strength is better than decrease strength. Or reduce sensitivity of strength to environmental changes, especially moisture changes. To increase or decrease permeability. Permeability, increase or decrease, my John say, actually it has to be decreased, not increase. Well, it depends upon what type of construction you are doing. Sometimes you want water should move in that, that's also possible. To reduce compressibility, means strength should be increased, only then compressibility can be reduced. Soil has been successfully used, soil stabilization has been successfully used in all types of engineering, problems, but its most common application is strengthening of highways and airport pavements. And there are methods which we'll discuss, we had already discussed, we'll discuss further, because it's very important, soil stabilization, and that is mechanical stabilization, cement stabilization, lime stabilization, bituminous stabilization, membrane stabilization, electrical stabilization, thermal stabilization, chemical stabilization. There are 8 more, let's say 8, so old book. So mechanical, cement, lime, bituminous, membrane, electrical, thermal, chemical. Got it? Mechanical, cement, lime, bituminous, membrane, electrical, thermal, chemical. These are all stabilization methods. We'll go into them one by one so that we can understand something better than nothing. So we'll say this is very important part, and then investigation, of course, much more important part of that. So there will be something we'll do in our next talk, and I just want to give background of this only, not in details, so that we can understand what is happening in soil world. So you all know that. I'm not saying you don't know that. You are structural, yes, yourself are calling, I'm not calling. I'm calling myself filling and non-structural. It doesn't make a difference to my health. I'm still not structural because he is an engineer. And only point that now, because it's already 4 hours 23 minutes, I would like to say, as far as this continuation of discussion, this continued deliberation, you can talk of this soil as an unexpected part. I started because of I felt people are having deficiency in basic knowledge of soil, which is very important from every point of view in civil engineering. And if you lack this, again I am stating, if you lack this, you are not able to do your job rightly. Designing is one part, but soil design is also integrated part of structural engineering. If you design foundation, I don't understand how you can design foundations. How can you design foundations without having thorough knowledge of soil? I can't answer this question. You can think on and answer your questions without understanding conduct of soil, behavior of soil, current and in future times. How can you ensure that your foundation you are delivering in drawings is accepting if is meeting those requirements which you are not clear with? That point is very worrying, very concerning, and therefore I have to make sure that I am able to share with you whatever is possible to be shared. And with that, I think I should close today's talk because it's already around 4:25, and I have to close. It's already 7:52, and I think it's time to go. We hope that you friends, I'm sure you may not be taking interest. I'm sure first because you are only inclined to modeling, inclined to running analysis, inclined to, you can say, designs based on StatPro or ETAP, where you are dependent on that. That should be, I'm not saying no, but basics you should know. Same thing, basics of soil you should know. You should not say, I want this software of soil mechanics and I want to use that. I don't support that, at least for soil, because it's human angle that's more important rather than software when structural designs with soil are concerned, just like we do in machine foundations designs, where you take soil also into consideration in foundations. Soil and also soil water combination is very important, which must be taken care of, which may not be able in these books or references, or in, because these are all foreign books I have gone through foreign catalogs and in whatever possible way through reports or something, and sometimes we get some information from those documents, which is very important for every and soil water mobility, and you can say chemicals with that move, and sinking of remote areas when you pump out water, as we discussed in dewatering cases. Dewatering, which also a part of foundation engineering, you cannot isolate that with that, because when water is present in soil, you are already lost a strength of soil. You have to manage that, and area has to be kept dry. Otherwise, you cannot do a foundation in no case. And that water movement around that foundation, even if you're tanking of that very well, you do protection of that very well, that water is going to impact your foundation, come what may. You can't avoid that. You must take that factor off into your consideration while you design a finalized foundation, and also when you consider soil movement, soil action with that, because soil will damage with water combination. It will damage not only your building, it can impact or adjust in the structures as well. It has happened just because of water flow. Of course, I'm not talking here. There have been impacts elsewhere as well, and you sorry means capacity of water, and environmental impact on soil because of that water. How much drawdown is there? Is can be excessive drawdown, or how much pumping you can do with what discharge of speed, discharge quantity after pumping can be. Which pumps you have to use? You have to use open drain system in that foundation, or you have to use well point system in that foundation. It depends on type of soil, and how many stages can be maintained, or you have to go to deep drilling of that. Means so many points are considered in advanced understanding of field engineering. So field engineering includes design aspects also on operational front, may not be original front. So we have to consider, sub-design, you can say it's a part of sub-design in field engineering, which is more important because it leads to construction uh, in whatever way these problems do appear in, and we have to understand those problems, analyze those problems, solve those problems, so that work can be delivered in practical form, complying with requirements of designs and specifications. And we can say we have met what designer intended to get, because designer knows purpose of that building, that structure. It's designer who knows complete intention behind that. We are only communicated, but what designer kept in mind while designing some structure, that's more important. And are we able to do that, or designer is able to understand what we think of how we do that? That is also very important point in engineering, civil engineering, because civil engineering is not actually dependent. Human factor, design, mind factor, thinking factor works many times more than codes in construction. Possible there are so many problems on sites, particularly major sites, which your designs cannot meet immediately when information comes in from site, feedback from this is site problem. Then we have to resolve that problem again and see where we're wrong. We can learn lessons from that. With this, thank you very much. I close this today, and we'll see again. I'm not getting any feedback from your people. Really, I'm very surprised with that. You people are not taking any interest. Fine, don't take any interest. I'm doing my job. If you take interest, I'll be happy. That thanks very much. Once again, I'm closing this today's talk with this on both YouTube as well as on Facebook. I am producing simultaneously this video on both sides. So thanks once again, and I think actually no, and YouTube studio closed, and now I'm going to close this as well. Once again, thank you.